bridge design series session number 5. Actually, it should be number 5 in my presentation. I had to change that one. The part 2 about the bridge loading and application. I think you got a couple of slides. I always have this one. Up to now, we discussed, we finished 4 sessions. The last sessions we discussed about bridge loading and its applications. And today's sessions, we're going to cover the rest of the bridge loads and applications. Yeah, just give me 1 second, please. I think I'm not sure I open up the wrong file or not. Just give me 1 second, please. I just need to check. Yep. Looks like I haven't updated the sorry that I haven't updated this couple of pages. Yeah. So I think you got a right one in the flyer. In the previous session, we discussed about bridge loading, some of the bridge loading and their applications. In the previous session, we discussed about different load types, dead load, superimposed dead load, and the traffic load. We spent quite a bit of a time about traffic loading. That is the primary load case we use in the bridge design. And then we talk about the other load generated due to traffic, the braking and centrifugal force, the way these loads are used in Australian standard and in Euro code. Then we discuss about when the trucks are moving before we enter to the bridge, just behind the bridge abutment area, the earth pressure due to a traffic load. Then we discuss about the thermal effect. I think this one, last time I promised I'm going to do some calculations and give it to you about thermal effect due to differential thermal effect through the bridge cross sections. I haven't done that one. Maybe in the coming days, I will include them in the presentation in the resource folder. So I have already uploaded the presentation slides to Google Drive. I think every one of you can now access to the presentation slides. So today's session, so before I start, today we're going to discuss in the rest of the bridge loading, especially creep shrinkage, wind load, earthquake load, flood load. These are kind of environmental sensitive load, and then these loads has been having a lot of impact on the bridges and the people day-to-day lives, as the engineers and researchers try to understand how to evaluate them in a right way and how to use them in a proper way when we do the designs. But it's been a long time, and still we don't have a actually proper understanding about all these loads what we are going to discuss today. And the other thing, because the about the wind engineering and wind loading and earthquake loading, it's related to what we call structural dynamics. I know there is not much like if you are a structural engineer, you don't get a good opportunity to learn about structural dynamics. So then I spoke to my professor who taught me about more than 25 years ago about the structural dynamics when I was doing my master's. And he was kind enough to deliver a lecture for us about the wind engineering and earthquake engineering. So I spoke to Shiromal as well. So he was kind enough that I think part of this bridge design series, we're going to have that lecture. I asked him to at least to deliver that lecture for 2 hours, because otherwise you can't learn much from him. His experience in the research and the actual application in the in this area of engineering is one of the best expert with my knowledge at the moment, working, teaching and doing a lot of work. Yeah, he's from AIT. I think his name is Professor Penan Vanachai. If you Google, you can see. I think some of you, if you studied in AIT School of Civil and Structural Engineering, where I graduated some time ago. So I think you already know the person I'm talking about now. He's a really good teacher, and he could have the really massive experience, and another thing, he can teach very well as well. It's all good. So the good thing is he's happy to deliver that lecture. So we will organize that one most likely. We will have that one in next month. Yeah. So then we jump into our presentation. Today we're going to discuss about restraint loading, creep shrinkage, and then the earthquake, wind loading, flood loading, differential movement, support movement on a bridge, and the barrier collision, and then finally the load combinations. This whole session, the most of the discussion I am focusing on actually based on AS 5100, Australian Design Standard for Bridge Design, based on that one. But there are the Eurocode and even the British Standard, they're all the same. There are same similarities. Before I start session today, I just want to mention, I think the last week when I was explaining about the live load models in Eurocode. I know most of you know in Sri Lanka about Eurocode, that Eurocode use characteristics values, and those is a bit different to what we were using in Australia. Like we said, I mentioned the live load, you have to magnify to get the truck and the bridge interaction. So, but in the Eurocode live load model, that's already incorporated into. And the other thing, the loads are very similar. There was a significant contrast I saw in the A160 live load model versus LM. I think that is LM2. LM2 model A400 loading in there, but yeah, the final outcome would be more or less the same. When I looked at the load the load factors and the dynamic amplification, so the outcome more or less the same. So the both the code application are the same. You need to understand the principles, then you can apply that one. The other thing, the one good thing in the Australian standards, because we have 9 volumes for bridge designs. We are using, I think, we have one volume for each section. For example, there's one design sections for the bridge loading itself. So if you are a designer, you just go to that document, because everything is in there. But for a Eurocode, it's written for a lot of countries, and then it's got it's got a bridge building and so many other applications in the same place, because when you are navigate that one, you may find a bit difficult. But I'm sure with this the presentation I am doing is going to be helpful for you. And I thought I need some volunteers. I already got from CSEC the one volunteer to I'm planning to write a small booklet for you guys to work on the bridge loading and applications based on the Euro standard. They are a real calculation, so then sometime you can use as a guide. Another thing, because the last couple of sessions we did, we just keep discuss, and I provide you a lot of information. I thought like the one session I'm going to discuss with you is to do actual calculation. So I'm going to give you an assignment based on up to now what you have studied, and then you can come up with your own solutions. So then in one session we discuss how we're going to calculate, or how we're going to, whether if you understand the session I already discussed, then you would be able to answer those questions. So in that way, I think up to now what you have learned and what you participated, you can see some outcomes. So then I will start today's session. The minimum restraint loading in a bridge. Why we need them? That's the first question. So you can see this first picture. You saw this one before. The impact on a barrier, the truck come and hit this one, right? So this truck, about 70 ton, is moving about 80 at least kilometers per hour, and it's come and hit this barrier. That momentum, you can see this truck still in here, that impact force need to be absorbed by the bridge, right? Because if you do not have a system to restrain that, the load on the bridge, this deck will be move away. You can see in the second picture, the earthquake effect. Because of the earthquake effect, you can see this whole the box girder kind of a bridge, it is crushed. And if you see the third picture in here, there's the collision in the bridge substructure in the column. Because of that, if you not properly restrain the superstructure, that's impact will cause this superstructure to move, or move. Even if it is a move by 20-30 millimeter, it's going to have an impact, because the bridges are sitting on a bearing. You can see in a flood event, when in this bridge, because of the flood forces, this pier is tilted, and you can see the aftermath is what happened, that the bridge superstructure is tilt. If you properly restrain this one, the outcome would have been different. And the other thing, this is covered in the Eurocode. When you are driving on a bridge, so you're supposed to drive on a lane. If you brake, you're supposed to brake on a straight in the longitudinal direction of the bridge, but it doesn't happen that way. You can see like this first picture, you can have a situation the people can break in not in the longitudinal direction, but with some angle. And the other thing, when you are driving on the curve, there is a massive centrifugal force that push the bridge to a transverse axis direction or transverse direction. So all these reasons, and we need to restrain the bridge. So if I summarize this, bridges are subjected to lateral loading, of course, the wind, earthquake, flood, centrifugal, collision, braking. The excessive settlement like a tilt and a skew bridges. The bridges are not always 90-degree, the bridge abutment, they are skew. That all, the thermal creep and shrinkage, that all cause the lateral load on the bridge. So then to prevent the bridge superstructure dislodge or excessive deformation in the bearing, we need to provide the positive lateral restraint between the bridge superstructure and the substructure. I would like to emphasize this one because people are spending millions of dollars in the scale of massive sums of money to build even a small bridge. And sometimes the designers and contractors, they don't like to do a very small structure. That is one of in the performance wise, that is one of the most important, because some designers, even they think it's not required. I design my bearing, I do this, I do that. It's all good in the computer model and it's all good in the calculations you do, the assumption you make, but in the real situation, like people come and hit a bridge, you can't say my impact load, I assume that value, the real one is different. And those situations, a lot of uncertainties, even if there is a 1% chance, yeah. So then that is got a significant impact on the final performance of the bridge. So now to make sure that the bridge is not, because of this lateral loading, the bridge superstructure is not dislodged or move, got a significant transverse movement, we provide what we call the lateral restraint system. So when we were designing in Australian standard, the lateral restraint system is a must. So you have to design that one. It's a 5% of the dead load or 500 minimum kilonewton load. You need to design your bridge to restrain. The vertical restraint is not a problem because especially the bridges are so heavy. And then the form of lateral restraint we provided in the bridge is a form of concrete block we provided between the two girders. And we leave this one. This lateral restraint block construction is very hard actually in the sides. It's extremely hard to build this element. You can see in the plan, it's between the bearing and between your girders. And so they got a significantly very complex detailing as well. So we need to maintain 10 millimeter gap between your girder and the bridge as well to make sure that your bearing is not moved by 20-30 millimeter. Then you have to replace and jack the bridge to replace the bearing to make sure that, yeah, this is the construction is very difficult in terms of the material you need to restrain. This one is not much, it's very little. But bridges like what you can see in this picture in the balanced cantilever bridge and this continuous span post tension bridge, if you got your girder and your superstructure and substructure is integral together, so then you don't need the extra lateral restraint. The bridge itself is restrained. So in this situation, you don't need a lateral restraint system in the bridge. And this lateral restraint system we provided in this terms of concrete block. Sometimes we used use a steel box. If you design the a steel bridges, we provide the lateral restraint with the what we call the bearing box within the bearing, and the will restrain that one. And we use the form of dowel because most of the bridges we have a cross beam at the end. That cross beam we can dowel with the bridge substructure. And the we use the bearing itself, like if you use the fixed bearing or guided bearing, import bearing, is provide the lateral restraint system. And then normally we provide this one mainly for the bridges articulate or support on elastomeric bearing. This system is quite important, providing a lateral restraint system or lateral restraint block that will help you, because this bridge can be subjected to significantly large lateral load, and you don't want to worry about your bearing is moving, because a lot of designers and a lot of people argue the bridges are so heavy, the friction between the bearing and the bearing surface and soffit of the girder is sufficient to restrain that one. But most of the people, they don't know when they were really build these bridges, those assumptions you make in the design office, you can't achieve 100% in the site. And therefore, providing this detail in the bridge, though it's a little bit difficult to build, but it's not so expensive compared to the other, the cost of the bridge is really good for the performance of the bridge. Yeah. Any questions up to now? Yeah. So then I will go to the next section. We're going to discuss about the creep and shrinkage. So at the beginning, I just need to tell you this is an area, I think it's more than 100+ years people doing experiments and doing a lot of modeling, a lot of testing to understand this one in a proper way. Yeah, a lot of the formulas has built, a lot of relationships has developed, but still I think the creep and shrinkage actual behavior and what we do in the calculation, sometimes you find a significantly, there's a significant difference in there. So I should say, you can't go and say what you did in your calculation is not right, but the assumption you made is not right. I think you can't complain like that, but we had to find the way to fix that problem in the site. So the creep and shrinkage is a common thing everywhere you deal with concrete, and the shrinkage of concrete is happening at the early stage of the construction. It's a time-dependent deformation of concrete caused by the drying or hydration process, and because of the shrinking of the concrete volume during the hydration process. The creep is the other way around. Creep is a time-dependent deformation of concrete under sustained load. So what's happened is they increase the strain under the constant stress. You know, when we were designing post-tension or pre-stress concrete structures, we got a opposite, we call the relaxation as well. So it's very important. For example, in a bridge, all the bridges we design as a composite, because most of the bridges we design as a composite structure. The steel concrete or concrete we design as a composite. So then after the deck is hardened, I think last week I spent some time to explain you. After the concrete deck is hardened, after that we build barriers, and then we put overlay the bridge, the asphalt layer. So all those things, they add together, they are sustained load. That's the throughout the design life of the brick. These are the very simple example for the sustained load. What the people understood about the creep shrinkage thing, because of the creep and shrinkage, the strain will keep increasing. Yeah, I just put this is not the exact fig diagram, a representative diagram for you to understand. The creep shrinkage will increase over the time. The way we accounted this one is using the initial strain in the mathematical model. We use initial strain, we can calculate that, and then we multiply from a factor that's depending on the time. We call the design creep coefficient. We're going to discuss this one a little later in detail. In general, the creep strain will increase over the time almost 2 to 4 times. That's quite significant. And the creep in the concrete is depend on a lot of parameters. Some of them are the material composition, your concrete mix design. Like most of you know, the olden days, the concrete, they construct using 124, 1.53. So the different kind of a mix design. So 136, all this mix they use and then put water and cement, and then you mix using showers, and we then pour the concrete. But in the modern day concrete, so we use there are a lot of things develop in the concrete material industry. So now the concrete we develop and we use in the industry for the brick construction and the building construction, for the construction industry as a whole, is much better performance, have got a much better performance in terms of the creep and shrinkage. So you can be happy. And the creep and shrinkage is the fact of the size and the dimensions of the bridge element we're going to consider, and the age of the concrete when you apply the forces on the bridge. For example, the pre-stressed concrete construction. So for example, in Australia, so we stress the girders today, and the next day we remove that one from the mold. Yeah, with we use the heat curing, and then we get the quick concrete strength. 50 MPa concrete, we get a 37 within a day, and then we cut the stress bars and we started fabricating the next one. And then you can bring that girder to the site and you can place on the girder and you can start your construction, but we don't do that one because of the creep effect. So though we cast the girders so quickly, but we let that girder to gain its full strength. But if you need, you can do that, but you have to design for that one. And the creep and shrinkage is so especially creep is going to affect the sustained loading, as we discussed in a bridge deck. The quite obvious sustained load is the barrier overlay, a drainage pipe, or any other things you attach to the bridge deck is always acting as a sustained load. So how to evaluate the creep shrinkage? As I mentioned, use empirical methods in the design standard. I want to tell you, because when I was doing my master degree, in the advanced solid mechanics, when I was learning, I knew exactly how this mathematical modeling in creep shrinkage developed. Yeah, from the first principle in mathematics. And those models actually doing experiments, we're still using it. And when we use them, we are doing only estimations. Yeah, I put the word only estimate, and it could be wrong because even the code itself say you can have a plus or minus 30% range, your creep and shrinkage value. So that means if you depend on your type of bridge you're going to use, you need to pay a special attention to that one. The plus or minus 30% range is quite a significant, that means 60% variation in that the estimate you make. And how to use them, we use simple method. And in the bridge design application, we can convert the creep strain to a temperature and you can apply, or else if you use the modern day software, for example, like Midas, it's built in the program. You can use a time dependent analysis. You just need to explain what is the parameters, required parameters and application of loading, etc. If I summarize the creep and shrinkage, what you need to understand, the shrinkage is happening in the early stage of the concrete. If you do a proper bridge constructions, most of your concrete structures you have to cure for at least 7 days in the bridge. So some of the exposure environment, like if it's exposure environment B2, let's say if you build a bridge in a Colombo area, your minimum, I say in the Colombo because it's close to the sea. The close to the sea environment in Australia, we classify as a B2 exposure environment. In those type of bridges, we had to cure at least 14 days. So if you're not properly cure, even myself, we have experienced because of the shrinkage, you get a cracks on your bridge deck here. And then because of the creep and shrinkage, if you are not properly designed, this is, I have seen again, pre-stressed concrete bridges, especially when you construct the bridge and build everything, when you leave the bridge, after some time, bridge will be hog. You get a hog in there, you can see the impact when you look at, when you see your barriers, they are shaped like they got a camber, free of charge camber in the barrier. If you not properly detail them, it will crack. Because of that, you need to pay sometime it may not create a lot of design action in it. If it is a continuous span bridges, you have a significant effect. But if it's a bridges on the elastomeric bearing, in terms of the stresses, doesn't induce much, but in terms of the articulation, it's play a vital role. Because of that, you need to pay a special attention when you are designing a bridge to creep and shrinkage. You can see this in this figure. Still, I'm in here. In this figure, I got some dot line, right? This creep and shrinkage curve over the time, this because initial strain on any structure you think of, that's a constant. So then we use the creep coefficient factor. That factor is a vary with time. You can see over the years, is according to the modeling, after certain years, like after 5 years, it's hardly change or increase the creep factor. Like you can see the first couple of years, it's starting from 0 to go up to 1.5. And then after 5 years, it's becoming 2. Then after that, next rest of the bridge life is jump up to 2.4. It's very little, or 2. Yeah, it's less than 2.4 according to this graph. It's like a 2.2. You can say then when you are designing and detailing a bridge, you need to pay quite close attention to this one. The bridge construction is not going to happen overnight, because most of the project, it will take at least 1 or 2 years. Like if it's a large project, sometimes it may be 1.5 to 2 years, let's say 3 years. After 3 years, if you say in the bridge construction finish after 3 years, you can see before 3 years, if you look at your creep shrinkage in this diagram, this number is about, creep factor is about 1.8 in here, your final number is about 2.2. So if you look at the 2.2, the 1.8 divided by 2.3, this is rough number. So 80% of this creep and shrinkage is occurred, especially creep, before you open your bridge to the traffic. The reason I am telling you this one, when you design your bearing, when you calculate this one, a lot of people, they don't understand the bridge construction. We install expansion joint in the bridge at the end. Because sometimes when we were doing the, especially this is very hard to explain to the clients as well. And when you calculate the creep shrinkage values, especially in the articulation, because the creep will reduce the length of the bridge by a significant margin. So that length will affect your expansion joint size when you design it. So because in the bridge, you're going to install this expansion joint in the bridge, before you open that one to the traffic, you build everything, you build your barrier, you build everything, then only you come and build your expansion joint. So the installation time is quite close to the opening time. Because of that, when you install your expansion joint, so you got a section of the concrete, you got a block out in there. Then after that, you go and install that one. Because of that, in actual creep and shrinkage, especially creep behavior, is going to affect from this point. I put this dot point open to the traffic from here. Let's say 3 years later, after you start your casting your girder, maybe 1 year later. So then sometimes you need to pay attention. Sometimes you got a step in your design. You have to go your expansion joint from the strip seal joint to a finger plate joint. You will learn this one next week. That's make a significant difference in your bridge expansion joint design, performance, and the cost. Yeah, this is something we need to, as an engineer, we need to look at this one in a logical way. Yeah, that's what I put this figure and I show in here. I put that residual creep in this figure to show you that what is left in there when you open the bridge to traffic. That's where the expansion joint will count actually this residual creep. Yeah. So sometime if you come across these problems, so you can look at that one very carefully. And then the only thing, if you go in this path, you need to make sure your construction will follow the way you assume in your design. Then I discussed now why the creep and shrinkage is so important, because the member contraction. Obviously, affect the material properties. Makes sense. Like if a creep, because of the creep, the structure, the elongation increase, that means the curvature increase, that means deflection increase. In other way, you can say if you talk in terms of the modulus of the structure, the property, the strength of the structure is reducing, because that's why it's deflect. So that's what I put this one to make it more direct. You use the effective the modulus to calculate the deflection due to creep, and it induces additional stresses. You can see these bridges in these pictures, this balance cantilever bridge, this post tension bridges, that's increase the significant stresses in there. In addition to that, the balance cantilever bridge I mentioned to you before during my discussions. These bridges, we calculate what we call the camber curve. We build these bridges with the upward camber and let the bridge to deflect in downward. But when you are constructing this one long span bridges, it's never going to work that way. Yeah. And the effect of bridge behavior, performance, and articulation. Yeah, the creep and shrinkage will affect that one. And the member length, if it is significantly large, because of that one, the contraction and the effect, the deflection is going to be significantly large. And the main members are heavy in the structures because the bridge structures are very heavy. Then this matter, it's affect the deflection, it affect it add a lot of stresses on the girder. And the construction is time dependent because the creep is time dependent, shrinkage is time dependent, then the construction is time dependent. That will make your analysis sometime a bit more complex. Then for the construction, we do the construction staging analysis, especially to calculate the camber curves, and that will the creep shrinkage assumption, the way we manage them, handle them, have a significant impact on the actual bit construction. The creep shrinkage, whether you build the material composite as steel concrete or concrete, so still you need to consider that effect. Another thing, the creep shrinkage effect has another one, what we call the differential shrinkage effect in the composite construction. And the member dimension, the exposure environment is going to affect the way you, as I mentioned, the composition of the concrete, the area you're going to build. This one in Australia, we divided area because like up north is quite tropical, and like a place like Sydney is temperate. Yeah, in the middle of the country is arid environment. But for example, in Sri Lanka, so you have some places dry zones, and then some places like Anuradhapura, that area we consider as a dry zone, but the other areas we consider as a wet zone. So that impact the behavior of the creep shrinkage. And because the members are pre-stress and post-tension members we use for the bridge construction, they are strength, because the creep and shrinkage will impact the if I mention the word, the losses in the strand and the post-tension. So there are quite a number of things you can explain. Many points you can talk about. It's very important to calculate in a proper way to understand how we're going to use that one. And the other thing, because the creep and shrinkage, when you were using different design code, I'm sure for the Sri Lankan, for Australia, the design standards say you have to use these parameters, but Eurocode develop a general parameters. But I think those parameters, I'm sure, for the Sri Lankan context, you need to refer to the local annexures to get the right parameters to use in the creep shrinkage calculations. Yeah, because I think they are not so difficult thing. It's quite a straightforward. When you calculate the creep and shrinkage, I put this slide. We use what we call the parameter is the hypothetical thickness. This is a parameter. Yeah, it's defined, called hypothetical thickness. That's defined 2 times the gross cross-sectional area divided by the perimeter of the exposed perimeter of the member. You see, I draw these sections because if you go to a bridge, you got a bridge deck on the top. You can see the blue one, that's the deck bearing surface. So when you take a composite construction, so if you get I girder beam, super T beam, girder bridge, sorry, and your effective section, you can calculate like based on the girder spacing. So this is in the figure 1, you can see this is the exposed perimeter of the member. And the first one is a solid section, and exposed perimeter is UE, you can calculate based on your section dimensions. But if you go to the second one, it's a hollow section. It's a single cell box girder or super T girder. Yeah, it doesn't want to be closed like this, but you can have a closed box. Still, you got a 2 exposure environment. One is the exterior one, the other one is the interior one. this parameter, the calculation is defined. If you got an interior and exterior environment, the perimeter, you can calculate this UE value is equal to the exterior perimeter times half of the interior perimeter. So if you get a twin cell box girder, that would be exterior perimeter time each and every interior, half of the individual interior perimeters. So you can easily calculate this parameter for any cross section. You can calculate for any cross section. What you need to be really mindful when you use in the bridge, because if it is a box girder, you have this deck and you have wearing surface, then that surface we can't consider as a the exposed perimeter, right? Yeah, and that's what I clearly draw this diagram for you to clearly understand this one. Any questions up to here? No? Okay. Then I just do a simple based on AS 5100. How to calculate the shrinkage. I think if you go to Eurocode, the concept is the same. The shrinkage the shrinkage is happening during the hydration process, and they make the autogenous shrinkage during the chemical process, and then the within first few days, I should say, and then the drying shrinkage in the concrete. So this is how in the Australian standard is calculated. I'm sure in the Euro standard also in the same way. And then you can see it's time dependent, it's a strength dependent, it's that hypothetical thickness dependent. Hypothetical thickness is describe you as something that the exposed environment where the creep shrinkage and then your concrete surface is exposed to the environment, like for then compare against the size of that one. We use the cross-sectional area. Please remember that the unit of this one is in millimeters. And based on these parameters, you can calculate for creep and shrinkage for any concrete element. Yeah, it doesn't matter what design code you use, the way these parameters present in the design code. So don't pay too much attention. You need to understand it's time dependent and it's the hypothetical thickness dependent, means the cross section, and all this thing, they make it simplified. All the points we discussed before. Yeah, that's what you need to understand. I just put this calculation for a shrinkage. I did a calculation for you to understand autogenous shrinkage, how much, drying shrinkage, how much, for a 40 MPa concrete strength with the hypothetical thickness 150. I did this calculation for Sydney. In the Sydney, the parameter basic drying shrinkage is 800 microns, and the factor is related to the location the environment is exposed to. It's a tropical and near coast. That value is given in the code. Based on that one, this basic shrinkage factor is becoming reduced to 800, becoming 272. Because when we were calculating this, the shrinkage and the creep, we need to have a base. That's what they started with. Yeah, that's what they started with. And then when you calculate this one, that is what I want to explain it to you. I just put the times, the day 1, 14 days later, 1 month later, 3 months later, 1 year later, 30 years later, right? The 2 weeks later is more or less like when you construct the bridge deck after you finish your curing process. 14 days later, you get total shrinkage 153. But if we looked at this autogenous shrinkages that we call this happening in the early stage, you can obviously see this one. The maximum value it could go is depend on the code. In this particular concrete strength, the maximum autogenous shrinkage can be 70 micron. You could, it just happened less than a month. Yeah, it's happened very quickly, right? In the process, you can see that after 30 years, the shrinkage value is becoming 437, but you can see it's 1 month. After 1 month, from the total, more or less 50% is finished. If you go to 3 months, you can see 300 over 437 is about 69% or 70% finished. Then if you go 1 year, most of the bridge construction will go on more than a year. You can see it's more than 87% is occur in the bridge. That's again, I go back to your articulation and calculation thing. You need to understand that what my advice for you is, it doesn't matter what code you use. Yeah, they are straightforward because it's clearly described the approach. You need to calculate them with the parameters. You develop this table by yourself and look at these numbers and draw the graph and see with the time the way the creep and shrinkage behavior in your particular bridge element. Understand yourself, appreciate yourself, and then over the time, because bridge construction is happening over the period of time, then you can get a better understanding of where I'm standing in terms of the creep and shrinkage. Yeah, that's the message. I just want to give it to you because the using the code equations are quite straightforward. Similarly, the AS5100 is described the creep. It's also started with the what we call the basic creep factor, and that's evaluated based on the different concrete strength. You can see the olden day we use 136, then 124 mix, 20 MPa, 25 MPa. These mix the creep is quite high. But if you see modern day concrete, 50 MPa, 65 MPa, 80 MPa, this basic creep factor is quite less, because the rest of the values, these multiplications, right? The rest of the multiplications impact that, but the baseline you are starting with, you can see 5.2 against 1.5. That's what I said. The modern material technologies in the concrete technology will help the structural engineers, because this one is a less of a problem. Yeah, even in the future, it will be much better, because the technology of the concrete technology is changing significantly. And as we mentioned, the one factor is the creep is always affect with the sustained load, because on the structure, when you apply the load, that sustained load will impact the creep. I'm not going to discuss about the creep behavior, the secondary creep effect, and those things when you apply load, when you remove it, like some certain bridge construction, for example, balance cantilever, those things. If you are interested, if you are doing a problem, if you have any specific questions, we can discuss. And then all these parameters, define this important parameter. What you can see is a time dependent. Again, it's our hypothetical thickness is important, and then the loading, the age, the time when we load the bridge is the matter. So these are the main two key elements you need to be mindful. And with that, we can calculate the what is the creep factor. This is a creep factor, as I mentioned. We increase the instantaneous creep or the initial creep, the initial strain by this factor. You can say again, this 28 days means I apply the load after 28 days. When I just let the concrete to gain its full strength, straight away I loaded that one, and then I calculate what is the creep factor for 40 MPa concrete at the same environment we discussed, the hypothetical thickness 150, and then the in Sydney area, and then this calculation shows it goes up to after 30 years is increased, the creep factor increased to 2.026, or else is increased the initial creep, initial strain by 200%. That's the word. I just want to highlight this one. You can see after 1 year later, in bridge construction, 1 year is not a big period of time. After 1 year's time, you can see the creep in the structure. For example, if you, after you construct your barriers and the asphalt, because the barriers you build, after a couple of months later, at least 4, 5 months, 6 months later, only you going to put asphalt and then the open the bridge for traffic. After 1 year later, you can see the creep factor increased to 1.7, and from 1 year to 30 years increased from 1.7 to 2, that means 0.3. If you look at this one as a percentage, 0.3 divided by 2, right, is less than 15%. The one I drew in this picture, you can see in the first diagram. Yeah, after you open your bridge, what you got in here, the residual, the creep is quite less. Any questions up to here? If I summarize this creep and shrinkage thing, what you need to do when you do a bridge design, don't use the code blindly. Pay a bit of attention, calculate this table, and sit yourself when you are building bridge where I'm standing, when I'm putting my load. You don't want to you don't want to go back and do all the calculation exact date. Okay, I'm going to put the barrier on that date. Then this is my the age of the bridge is 28 days, no 56 days, 3 months later. You can't dictate the construction terms to the contractor. That's not right, but you can use your general understanding to make judgment. Yeah, that's give you a quite important, when you design and do the calcs, it's help you a lot. Yeah, and I have this saying all the time. When I was reviewing some designs, especially the segmental box girder kind of constructions, the designers put, okay, we were moving massive gantries. We moved this gantry 3 weeks time to there. My age of we cast the box 1 week before, and we bring here and we place it, and then okay, my creep and shrinkage is happening from 28 days to 30 years. I got my numbers and do the designs, and you do all your assumptions, and then when you submit to the client and everybody get shocked. Okay, you got that much of deflection, creep, shrinkage. It's got a massive effect in your bridge. Anyway, because the actual construction, it won't happen. For example, in the segmental box girder construction, most of the time you cast your box. Sometimes you leave at least 1 year to 6 months in the yard or somewhere near the site before you erect them with the gantry. And to construct the one span, everyone say it will take 2 weeks, 1.5 weeks, and all these numbers never going to happen. If you say 1.5 weeks, you can say at least 4 weeks. So these actual real construction behavior, when you calculate, then before you erect in the segment to the bridge, the the creep shrinkage is all happened. There is nothing left in there. Yeah. So therefore, that's why I said it's depend on the type of bridge to bridge. You need to pay attention. Another thing I want to share with you, this one, if you are using a pre-stressed concrete girders, if you leave them for months and months on the yard, so you get girders with pre-camber, a significantly large pre-cambers. Sometimes you will have a real you have a real problem to get your bridge alignment right in the side. Yeah, that's, you need to be really mindful. I think we will later on, we will do some calculation to understand this one in a better way. These are the things when you play with creep shrinkage, especially the pre-stressed concrete girder cambers. The period you left the girder after you cast, it's going to affect us significantly, because we set the bridge alignment first. Based on that one, we set all our levels, and we are building the bridge from bottom up. You do your pile footing, a girder, bearing, all these levels we set, assuming this is the final finish level of the bridge. Unless otherwise you change your bridge alignment, if you realign the bridge, otherwise you have a significant impact, especially your bridge deck thickness. So therefore, you need to pay a special attention in the creep and shrinkage calculation in the pre-stressed concrete girders. Any questions? Any thoughts? All right then. Then we're going to discuss about the earthquake, but this one, again, this is a very quite a significant area, and country to country, this earthquake design take a different dimensions. For example, if it is in Japan or in New Zealand or US state of California or Indonesia or Philippines, the earthquake design is really significant. But as far as the previous, according to the history, according to the data, but in Australia and in Sri Lanka, the earthquake is quite significant, but not as critical as those countries. So you can see in terms of the design, that's what I say, the extent of the earthquake design, you had to go a significant area. For example, I was just attend the presentation just before started this one. They were talking about earthquake design, some of the designs they used in New Zealand, but that extent is quite significant. So in this presentation discussion, I'm not going to go to that extent. I'm going to discuss the scope within Australian standard. I think it is quite applicable to Sri Lanka as well. And you can learn more about the earthquake design principles and the way things built up in the Professor Pennant's lecture. And then the earthquake happened. What you, in this, like, attend the discussion you need to take home is that if you detail your structures in a proper way for the earthquake, I don't think any of these damages will happen to up to this extent. There will be damage, but still you can reduce the extent of that damage. You can see these pictures, massive destruction. Yeah, so none of these bridges you can use it. So you can see the one on this picture is interchange there. So you can't use that road at all, and the construction, you have to demolish them, you have to rebuild them. It's a lot of work, plus it's take time, and it's affect significantly in the economic activities and the people day-to-day life. So it's very important the understanding, have an understanding about earthquake design and design the bridges for earthquake loading. But the extent of this design is vary from country to country. So the when we were designing earthquake, like some bridges I show in here, this industrial ring road one, the pile toe level to the top of the bridge is 125 meters. The distance between the expansion joint go as long as 600 plus meters, and the girder span is about 66 meters. The other one, this a standard super T girder bridge, but still this bridge is built in a valley. The deck height is 24 meters above the ground, and then the length of the bridge is 300, and total height, if you go from pile toe, is about 40 meters. There and the extreme ends of the bridges, when you design in, the earthquake design sometimes may not govern your design, govern in the sense it may not induce large forces as the traffic load. For example, the primary load case, the primary load we design bridges, it may not as significant as that, but still detailing the bridge to make sure it's not, it won't happen like this. Even during an earthquake, if a bridge is slip, superstructure slip is not collapse. For you to go back and jack this bridge to its position, it's really difficult. We are talking about this one girder with the bridge deck is about 120, 130 tons. To jack this one and move that one, it's not easy. It's not like a carry back thing. Therefore, pay a special attention in your detailing. That's what I try to explain you in here and in the next presentation about bridge articulation, how we're going to incorporate this one in the earthquake design. That is very important. Yeah, we will discuss more detail while we were discussing about bridge design later. Yeah, the extent of this presentation, the information you're going to interpret, is very different, and because it's very specific for each and every country. But I think for Sri Lankan context, I suggest if you want to design for earthquake, I think you can use the Australian standard. Is quite detailed, and you can see now. Yeah, and I think that's quite sufficient, because the Sri Lanka is not in a earthquake critical zone. So the earthquake occurrence, if you Google it, you can go to, I think, earthquakes. Different countries have their own earthquake occurrence map, but I think there's a global one in US. I think from that one you can find the earthquake happening. Even a small earthquake happen around the world, they recorded at the US Geological Survey Center, if I is correct. So you can say this one. I just put this map for you to show. You can see in this map how many dots you can see around in here. Yellow dot, and then red dot, and close to brown dot. These dots are earthquakes. But the colors, the difference is, like a red dot is we measure the earthquake in a Richter scale. That one is greater than 5.1. We consider as a significantly large earthquake. It's happening in the land. Yeah, there are a couple of red points in here. So that means you can see that there are a lot of yellow points around here in the land. So you can see it's happening all the time. It looks like, then you need to be really mindful when you design your bridges, long structures, and then you have to be you pay attention to the earthquake design. And design in the sense is not the analysis and find the reinforcement. It's more to do with properly detail them to make sure that it's designed for earthquake behavior. I should say the word behavior. What is happening in the earthquake? See, the earthquake is happen underground. Yeah, it's happen underground. It's release the massive energy. With release of that energy, develop a pressure on, I should say, the wave system within the earth, and that wave system is propagate all the way through. If it's happening in the sea, we are lucky because we have a dam on the top, that's the water. And then if it is happening on the land, because that wave propagate to the surface, if there is nothing in there, that surface that will vibrate and will leave, maybe crack a bit. But if you have some structure in there, what happened to that one? Because the earth is moving, there is an inertia in that. If you intercept that inertia, the wave energy, if you intercept your structure, your substructure, so that cause the inertia force induced into your structure. It could be a building, could be a bridge. So we are working on the three-dimensional space. That inertia force will translate into a bridge as a longitudinal force in the longitudinal direction or transverse direction or in the vertical direction. The lucky thing is the earthquake is happening, is peak quickly and then damping out within a short period of time. It's happening within short period of space. Because of that, your inertia force or your vibration on the bridge is happening very short period of time. But only thing, the extent is very important, right? We do analysis and we do design. We say, okay, it's longitudinal govern, lateral is governing, and then vertical is governing. But in actual earthquake, everything can happen in three-dimensionally simultaneously. We never know. But we need to make sure that from the information we have and from those data with our experience, we need to design the structure to absorb this inertia force. In the same time, we need to detail them properly. The concepts, the code is developed based on like this. The code say, when you are designing a bridge for earthquake, first identify what is your bridge looks like to be, what is the bridge performance requirement. I'm not going to explain it here, I will explain it in the next one. Then see what sort of bridge you're going to build. See the ductility, what sort of foundation system you're going to put, and what sort of material you're going to put your pile. Is it clay, or is it a soil, or is it a rock? If it's a strong rock or weathered rock, if it is a soil, if it's the steep clay or subsoil, all this ground condition, yeah, you need to understand that. And then, because as I mentioned, because this earthquake and the wind engineering one, we're going to have a proper session. In that one, Professor Pennon will explain to you in detail about this thing. That's what I'm not going to explain this one in detail. I'm just going to talk about the code context. And then you need to understand, if you know your structure and your ground, everything we know, because when we are designing a bridge, we do investigation, we have understanding. Then we need to understand from the analysis how our bridge is going to respond to the earthquake loading, or how we going to go together, how we going to design our bridge and the earthquake loading together to make sure that it's not going to collapse like we saw in our first slide. Then after this analysis, we design and detail our bridge and bridge element to absorb this inertia load and make sure it's not going to crack or it's not going to collapse, or it's not going to dislodge. You trust me. When you do the earthquake design and detailing, you don't want to spend hundreds of thousands of millions of dollars to achieve this thing, right? There are simple details. I will discuss this one a bit more with the bridge articulation, but there are some resistance from even a client, from sometime even from the contractors, of course, they don't want to do hard thing. And then even some designers, they think, I don't know, it's not required. This one is like that, this like this. To me, it's not the way you need to look at you when you design a single span a 25-meter long bridge against a 4-span 100-meter long bridge. Your earthquake design acts the detailing and the way you design for the earthquake for this bridge need to have the same approach. But when you come to the overall performance, when you look at the risk associated with this, nobody knows this force, the unknown force, you can pay a bit more attention to make it better. Yeah, that's I want to mention to you, because it's not you just follow blindly the code, or you just put that one tick the boxes. It's not that way. This is the area you need to make your own engineering judgment to make sure that you build the bridge for 100 years. This bridge is going to impact by an earthquake, not during my lifetime, maybe my grandchildren lifetime, right? It could happen. It could happen, and then that might destroy this thing, and then it's going to cost during that time. If I spend $5 million to build this bridge today, and at that time it's going to cost another 30 million to build that bridge. Yeah, that is the mindset you need to have when you were designing for earthquake. Please keep that one in mind. And we use all the structural dynamics modeling. This standard equation, mx double dot, that's the inertia force, cx dot, this is the damping force. If you got a shock absorber system, I think in the second year in your when you study mechanics, you study this equation. The kx is the stiffness part, ft is the earthquake load. It's time dependent load. We can solve this one. I think the general equation, we divided this one by m, then we call k over m is the w squared, and then c over m is equal to, if I could remember, the 2 beta w. And all these parameters, we solve these differential equations, and then we come up with so many solutions and so many aspects in analytically. But the earthquake force is luckily it goes up like this, decay like this. So then we need to see, when based on this code, in this approach based on the Australian standard, we see how we going to evaluate this, how we going to represent the earthquake loading is unknown. There's a lot of unknowns in there. How are we going to represent this one as a load, apply to our structure? Like, for example, we apply traffic load, right? So we use models, right? We use SM1600, we use the LM1 model, right? 600 TS load and 27 UDL. So like that, we have to develop a load system that we can apply to our bridge and then design the bridge. Let's see how we can do that. So the performance requirement will categorize the bridge. The performance requirements of the bridge dictate in the code we call bridge earthquake design category. Then from that one, if your bridge is so important, they categorize the importance level of the bridge. We have 4 categories, you will see. Higher the importance, then the earthquake, when the earthquakes are happening, we saw the earthquake maps. We develop earthquake maps. We call the the ground acceleration maps, and then we increase those acceleration, those inertia force, what we call, by the factor. We magnify that one based on the importance level still. And then, as I mentioned, the earthquake happened. We can, from the historical data, we can get the ground acceleration. The codes now is called the design seismic hazard factor. And of course, we want to know what is our foundation conditions, what is the subsoil, the earthquake force is transmitting through. If it is a rock, is one way. If it is the subsoil, that's another one. Yeah, of course. And then if it is a steep clay, is different. And the bridge, as I mentioned, the ductility of the bridge structure, like a continuous span bridge, or is a simply supported bridge on the elastomeric bearing. So from these, we can develop what we call the seismic response spectrum. That is like this earthquake force with the time, because the earthquake is time dependent, then your force you need to develop is a time dependent one. If you know the force, then you can analyze your structure. It doesn't matter, because if you know the force, for example, before all these computers come, all this algorithm come, but people still design the bridges for earthquake loading. For example, if you split this one into different time zone, if you apply this force individually, if you use the principle of superimpose, still you can come up with the solution. It's still possible. So we got a software to do that one now, but you do the analysis. This analysis also, you can see I link with the performance requirement of the bridge. Extent of the analysis we need to design in your bridge is depend on the performance requirement of the bridge. When you get your analysis, you calculate your bending moment, shear force, and everything. So you need to detail it. The detailing also is related to the performance requirement of the bridge. So then you first need to identify what sort of bridge this performance requirement we are talking about. You need to have the first understanding about that one. That all related to this performance requirement. So then I will explain it to you what is the performance requirement described in this category. There are 4 categories. Higher the number, higher the performance requirement. I will start with the higher one. Bridges and associated structures that are essential to post-earthquake recovery as specified by the road agencies, and major bridges whose operation is essential to economic viability at state or national levels. Okay. What is the post-earthquake recovery? Like a good example is the flood. After flood happened, you can see there's a cover in the piers. Like earthquake happened, we haven't seen that one. So when the earthquake happened, the bridge might be cracked. It might be the expansion might be jammed. The bridge deck might be dislodged. So you can't let the traffic to, or you can't let the people to drive. The post-earthquake recovery mean, if there's an earthquake happen, because the emergency services need to attend to help the people, because for them to use this one, the bridge should be usable. We should be able to drive through the bridge. And if this bridge, for example, linking, let's say the port to another industrial zone or to the airport, because we need that bridge to transport the people all the time. And it's got a massive economic impact if you let this bridge to damage through an earthquake. It's not acceptable. Because of that, if you have a bridge in the earthquake design category 4, that is the highest category we have, because that is the bridge we need to make sure that bridge is serviceable even after earthquake. There are two good examples in the world, I think. The bridges that can take any earthquake is, I think, the Akashi Bridge in Japan and in the Rainbow Bridge in Tokyo. Maybe during Professor Pennan's presentation, he will discuss this one. I'll ask him to explain it to you all. The things they did to make sure that, because in Japan, we got lots of earthquake, but still is post-earthquake recovery and economic viability is there's no problem at all in that bridge. It's same as the way they built. And in addition to that one, the category number 3, we call the BEDC in the sense a bridge earthquake design category, BEDC 3 in the sense. This bridge-led high volume of traffic is an important bridge. And this bridge is built over another highway. This bridge is connecting, it's a local road, but you are constructing over important motorway, right? What happened during earthquake, this bridge is collapsed onto your motorway, right? You can't use the motorway. So your motorway, you design all the bridges for BEDC or importance level or bridge design category level 4, but you are one on the top because they say it's not important because they're just a local road linking this town to that town. Yeah, if they have earthquake, they can use the other one. So what happened if this one collapsed to the motorway? You can't use the motorway then. When you design this one, this bridge, you have to design more or less in the same way. Only difference you can see in the later on, we call the damage control, and in the bridge design, we will call it can damage, but it's not going to collapse onto the motorway. Yeah, it's applicable for building and railway as well. So BEDC 2 is the minor bridges. It's not belongs to either one of these. It's in the bridge somewhere, nowhere. If there is some damage happen, okay, the people can use the alternative route. You got plenty of time. There's hardly not much traffic, not that important trucks or anything good or transport in between. Still, if this transport route, you can just detour a bit. You can still utilize. It's not in the urban areas, for example. And the BEDC one, okay, this one is not belongs to any one of these things. Yeah, let's say the access road to a local farm, especially in the Australia, like when we go to the country. Yeah, so you can have access farm to the bridge. It can be designed as to the BEDC one. And like I mentioned, when you were designing the bridge, I said this earthquake design, everything is related to this bridge earthquake design category. Now you can see how important to understand that one, especially when you are designing. It's not designing for earthquake. It's designing for particular structure to sustain that earthquake loading and for form, and make sure that we design and detail for that particular case, and that structure of our bridge is serviceable after earthquake. And the code also got this limitation I just want to mention to you, because it's used for conventional bridges, and the span only less than 100 meters, and the skew angle in the bridge less than 35. It's not a quite tall like industrial ring road. It's less than 30 meter high. The design effect is ultimate limit state. Is when you design building, you use both serviceability and ultimate, but in the bridge we use ultimate limit state. And overall stability and horizontal movement, there's a controls in this one. These are the limitation in the code. For example, if you design a cable stay bridge, so the approach is very different. Yeah, that you will learn a bit when we talk about the wind. And then, like I mentioned before, this design built on the probabilistic model. The return period, the annual probability of accident or return period, it's like we talk about this one already, like in the flood and the wind, 1 in a 2,000 year event. But if it's a category 3, it's reduced to, say, return period 1 in 1,000. If it's a category 2, it's 1 in a 500. If it's a category 1, basically we don't want to worry too much about the earthquake design. And then to calculate the earthquake, we should know the what is earthquake, what is the ground movement, what is the ground acceleration, what is the ground inertia, what is that force, because from country to country, I think they have a maps. So before, in the previous code in previous one, before this 2011 update, we call this one ground acceleration. It shows the percentage of gravitational acceleration percentage. For example, in Sydney, it's about 8%. And now in the latest code, we call dynamic seismic hazard factor, because this factor we're going to multiply from the importance factor or the probability factor we call. This the particular the maps were developed based on the 1 in a 500 year return interval. So then based on that one, if your return period is higher, recurrence interval is higher, so you need to magnify this one. These are all probabilistic approach. In our case, the BEDC4 is the highest category we use. That's, we have to amplify this ground acceleration 8% by 1.7. So if you get 0.08 times 1.7, it's close to 14%. So ground acceleration, the 0.14 G we use in that in the designs. It's not that's how it's going to correlate. You see the higher the importance level in the bridge, in the same place, you can see, that's what I want to explain it to you. In the same project, in two different places, in the same bridge, you can design you can use the two different earthquake approach to design the bridge. Level of importance, because the level of performance requirements is different in the same project you can have. So then from this one, we can magnify this, the hazard factor from the KP, and then we need to understand the ground conditions. Based on the ground condition, this code classify, because there are you can have hundreds of thousands of ground conditions when you are designing bridge. From in a one project, you have many different ground conditions. So then when you design your bridge for earthquake, place to place is different. And this code classify the rock, strong rock, and the rock. There's a classification on this one. Then it's called the shallow soil and the deep subsoil and the very subsoil. And the 5 classification of the subsoil. Based on that one, the code developed the 5 earthquake response systems. Yeah, that's because these are the simplifications things. As I mentioned, the different code, different approaches you can have for example, if you design a cable stay bridge, you won't use these approaches. You need to have a special earthquake design and analysis. Maybe sometimes you will use the different, you may use the actual earthquake loading. Yeah. So these subsoil information, of course, when you are designing a bridge, you do a lot of ground investigation. Our geotechnical engineers, those ground investigation, they classify into they compile into report. We call geotechnical factual report, geotechnical interpretive report, geotechnical design report. From that one, from the bore logs, so you can identify the type of the rock you're going to place your bridge foundation. You can see in here, this picture is in the it's not clay, it's clay and sand. Clay and sand. You can see this in the red is your bridge pier. You can see along this length, they are located in a different subsoil environment. And then the other picture is in the rock profile. You can see they are not uniform along the length of the bridge. These are the longitudinal ball of profiles I put for your information. Then these are the classification. How do you classify different soil types? How to identify the, for example, the subsoil class C, different if it is a cohesive clay, cohesionless clay, and that sort of thing. If it is a rock, how you're going to classify them, whether A or B or C, that sort of thing, A or B, that's all classify based on the UCS strength and the shear wave velocity. We do test to calculate that one, and then the thickness of the rock and other thing. Because I'm not going to go in detail this one, so you all can read through this one. So based on the geotechnical information, you can identify what sort of ground condition you have. Because sometimes you might ask a question, because if a bridge is quite long, let's say if you have a bridge, we call a bridge, if it is a 200, 300 meter long bridge, maybe it's okay to use the same earthquake response system. But let's say if a bridge, we call a bridge, if it is a couple of kilometers in length, so you need to have a different earthquake subsoil categories when you design the bridge, because you might encounter significantly different soil conditions in there. Yeah, because you don't want to consider in the earthquake design that one as a single bridge. For earthquake design purposes, you can have a segments. Yeah. And then you can see this is some of the bore log data. This is a good rock. You can see as a basalt. The back color one, you can see they are they got some crack in there, but so quite good rock. But the picture on the bottom left is the soil. You saw that this soil profile, one of the borehole information, but it's quite, this information is not on the top. It's a depth between 44 meters to 50 meters. And then the other one is the another one, the bore log information about the sandstone. You can see this rock is quite weak because it's fractured. You can see some section is quite good, but some section is really bad. So when you were designing for earthquake, you can see within this, when you go under the rock, under the underground, you can't see anything. Your behavior of the rock within the one section of the pile, it significantly varies. But you have to simplify your approach to design, but you can incorporate almost everything in there in the design. Yeah, in terms of the engineering, I think doesn't add any value as well. But it's, yeah, because of that, then when you are designing bridges, pay close attention to what sort of material you're going to what is your foundation, the material we're going to place in your structures. Yeah, have a look, and that's very important. In the next slide, you will see the bridge ductility also, as I mentioned, play a significant role. It makes sense because the earthquake is a ground. The movement, that inertia will be translated, we call the shear, as a shear to the structure. I would like to use the word inertia force in three-dimensionally. It's very different if you are building a bridge on a simple span bridge like this, a steel bridge, and then the standard eye girder and super T bridges on elastomeric bearing, with sometime with the link slab on the top, or the continuous force tension bridges. They are this bridge integral with the superstructure and substructure, like the first two pictures, and the other one sitting on the pod bearing. But the deck is continuous, and the ductility is different. For example, if you go to this continuous force tension bridge, that's got a higher ductility, because when you absorb the load, it can redistribute among the members, the between the column and your bridge superstructure compared to this I girder simple span bridge. We got expansion joint at every 25 meter span. Then this ductility, higher the ductility, then the better the performance for earthquake. Because of that, this ductility factor, you see our probability factor or the importance levels with that one, we increase the earthquake effect. With the ductility, we can go in opposite direction. So the better the ductility, and then you can redistribute your load. That's the way you can understand that one in terms of like a structural engineers. And then these all factors then be related together in the later state. The code gives you a guideline. So very this information provided in the code is not very little, but when you are designing and detailing, you have to pay, that's what I said, extra attention. What you are doing is not inputting numbers into the computer and get the output and then match this number. Actual load is less than the capacity, not that one. As I mentioned before, our importance category bridge earthquake design category 4 is the highest one. We call that one the service or immediate use performance level. That means the earthquake happened, because it's not going to happen for hours, a couple of seconds. The emergency crew to others, they can use that bridge. The earthquake design category 3 one, still it can be usable. It can damage. We call the damage control performance system. You can drive, but your expansion joint may be like a jam sometime, but still you can drive through that. It's not that your whole bridge deck collapse and then it's crack and twist and like you saw in the picture, no. And then ductility factor, as I mentioned before, the bridges we show in the first two, the fourth continuous span bridges, its ductility factor is higher. But if you go to the standard bridge, they are sitting on elastomeric bearing. That is it's low. It's 1.5 for damage control. It's 1 for if it is a immediate use in service, because there is no contribution from ductility, I should say. And I believe it's not mathematical thing. You understand the concept, why we were using. When it's a BD category 4, the performance level high, we up the hazard factor or the gravity, the ground acceleration. The other way, if it is the ductility is higher, so it can redistribute the load. Because of that, it can reduce. Yeah, because that's how it's going to do. It's not the numbers. You divided by 4 and multiply by 1.7 divided by 4. It's not like that. Yeah. Then what we're going to do, we're going to combine everything together. Before that, what happened when the earthquakes happen, the people they develop the spectrum. Because you can't really design for the actual earthquake for it's not that easy for you to design your structures. And then the designers came up with the models. Yeah. These are the models. I think most of the mechanical engineers, even you learn, I think this spring and damping model in the structural dynamics. So when you study in your second year or third year in the university, similar to that one, we develop what we call the design spectrums for earthquake design. Because as I mentioned before, the earthquake, that inertia force is happening, is go to a maximum force, then is damping out, the die down. It's the earthquake period. It's not hours, it's a couple of seconds. So then this design spectrum we use in our earthquake design. We use this spectrum as a force into our the time dependent force we apply to our structure, and we look at the behavior of our structure. So the Australian standard, as I mentioned, we categorize our ground condition because the earthquake force is depend on the actual ground, because it's generated from the ground. You can see if you started with the this, they call the acceleration of spectral shape factor, this inertia, the force. And if it is a good rock, if your substructure is sitting on a really good rock, right, the curve is on the bottom. If it is a soft soil, let's go to the top, and even the peak period, the extent of the peak period also a little bit longer. Yeah. Anyway, all these soil conditions, this earthquake load is going to die out, right? So now what we're going to do, we're going to apply this one to design our structure. Then, before we talk about, because this is just a curve, this one need to convert into a force. You need to multiply from your accelerations. So I'm not going to describe this one. This slide show how you can get this one mathematically. Yeah, you can. Yeah, this mathematically you can develop this one in here. The equations were there, and the seismic acceleration elastic horizontal earthquake response, they call this CHTF. This we show in the previous diagram, because that is not acceleration. To make it acceleration, we multiply that one by our seismic hazard factor, or before we call ground acceleration. So depend on the importance level, how important our bridge is, we multiply that one by KP. This makes sense. In our bridge, if it is the design category 4, the KP is 1.7. I should say that this is the Z009. This is in a Kayama area. The ground acceleration or hazard factor of the ground acceleration is 0.09. And then you can multiply this one. Then this diagram is follow the same shape, but when you convert that one into a percentage of the actual acceleration, you can convert that one into a force, because acceleration time the mass, you get the force. So then, like I mentioned before, the horizontal elastic, we call that horizontal earthquake response. If you incorporate with the ductility, because this is not multiplying from the ductility, it's divided by the ductility. So makes sense. More ductile the structure, like continuous force tension span bridges, got a higher ductility, then this effect will be less. So then we talk about the normal bridge, simply supported one. Then that one is, we got the ductility factor is 1.5. Then if you convert this K Z over mu, Kp Z over mu, that value, when you simplify it, is 0.1 or 10% of the gravitational force. So this force, if you multiply from the weight, right, you get the horizontal earthquake force on the bridge, but that will follow exactly this shape. It will follow exactly this shape. Suppose if someone doesn't want to use, some engineers, this one they use, they got one of these curve according to the subsoil condition. You can easily identify this curve, and you get that area under this curve, and you divide it by the time period 4.5. Then you use that average value as the acceleration, like a gravitational acceleration force, like in your, if you do a simple the models, you can use that one. Sometimes you use in your design. You see why in the we use always as a percentage of the gravitational acceleration. That's why we can straight away multiply this one from our weight W, that is in kilonewton, right? This is we get the percentage of gravitational acceleration. That means is already divided by G. That's why we can use the weight in kilonewton in here. Otherwise, you will go and then, because when I say use the word acceleration, you will change that weight to a mass divided by G again. It's already taken into account in here. So for example, in this particular situation, right, in this particular site, the gravitational acceleration, the earthquake force is about 10% of the weight, 10% of the weight of the structure. It's not like you get the total weight of the structure, get the 10% of that one, apply like a different direction. It's not going to work that simple way. It's bit it's bit different than that one. Then depend on the type of the earthquake design, we are doing a different earthquake analysis. I'm not going to go in detail to this area because I put those things for you to understand. I want you to understand it. You can convert the shape, every code you use, more or less the design spectrum or spectral shape factor. It looks the same. So you can convert that one into a the earthquake, the force, and then that one you can apply most of the computer softwares. I think they build those things into the system. Otherwise, you can easily develop and you can incorporate that one. So depend on the type of the structure, you need to do many different analysis. In the design Australian standard, they say sometime when we were designing for earthquake, we use only as a horizontal earthquake the force onto the bridge structure, but depending on the importance of the bridge. For example, design category 4, you need to combine with the vertical response as well. So the vertical response, the code say you use the 2/3 of the horizontal value. So use the same one, but 2/3 of that value. It could be different to country, like you can use a different value, but the Australian standards say use the 2/3. Yeah, depending on the type of the bridge earthquake design category, you need to select a different type of analysis methods. If someone would like to learn more about this one, I can give you a design a document. It's with the work example in there, hand calculations in there. So many things you can learn if you need. Maybe I will put that one in in the resource folder. You can go and download. That's give you the hand calculation in detail. If you are interested about, you can read through. Yeah, because this one you can get a more understanding, a better picture, a lot of things about when you listen to Professor Penn lecture as well. So this is what about the earthquake design. If I summarize this one, you need to know what the performance requirements of the bridge. What is the purpose of this bridge we are going to build? What is the location of this bridge we are going to build? What is our ground conditions, subsoil conditions? And then based on that one, we get the earthquake, the force, that's the inertia force, or that acceleration, the design spectrum. If you have a computer software, it's capable of analyzing that one, you can use it. That otherwise you can just do a kind of a iterative approach. For example, you can play with the average one, because we got a peak value, and you can compare that one against your natural period of the structure as well. If your natural period of the structure, let's say beyond this 4.5 seconds, then your average value you design, yeah, make sense. but your natural period is getting closer to this peak value, the occurrence in here, it's better to change that one. You check your design to close to this, the maximum value as well. Yeah, it's not the average value. When you get your the design spectrum, and then they compare your design with my experience. The earthquake is not going to govern the design. You will see that one when we go to the load combination part. Any questions up to now? No questions? That means you'll understand nothing. Huh? Any questions? Or is it clear, or can someone say yes or no? Because
yes, it's clear. No questions so far.
right. Okay, then I will get into the wind loading, because I think I'm not going to spend so much of time with the wind loading. The reason I think the first thing in when you study a civil engineering degree, what you're going to learn first thing in the university is to calculate the wind load, right? And it's depend on so many elements. Another thing, you're going to learn this one in detail again in a separate presentation. And the wind design is quite important, but I should say the wind design it's not governing in the most of the bridges in the when you design based on the Australian standard, but the wind design, the calculations and the extent, every code it got a separate design code for the wind calculation. It's very important to understand and then how to use it. And it's more critical in long span bridges, of course. Bridges in open sites, depending on the bridge superstructure and substructure, especially cable stay bridges, suspension bridges, arch bridges, they are quite critical for wind and the wind velocity and wind attacking angle and that sort of thing. And the bridge member shape, aerodynamics thing, and the terrain and where it's located, is in a valley or is in the middle of the city, or yeah, that sort of thing that's going to impact. And we discussed this one in the design, the return period. We talk about when we were designing the wind we designed for serviceability as well as the ultimate limit state conditions. The return period for serviceability limit states is 1 in 20 years. It's quite frequent, but the ultimate limit state is 1 in a 2000 year. But you can see the basic wind speed we started with. That one for the ultimate limit state is 48. The corresponding one for serviceability is 37. You know the wind force, the pressure. The pressure is always proportionate to the V to the power 2. Then if you divide 37 by 48, and if you get this, 37 by 48, square of that value is about 60%. The ULS value is about, the SLS value is about 60% of the ULS value. In other words, if I just get this one, it's about 1.7 factor of safety. That's the correlation between these two. In the wind, when in the design, we started with basic wind speed. Depending on the location, all those things, we're going to calculate the wind speed depending on the location, like a terrain and so many parameters. We're going to calculate the design wind speed, what we call that design wind speed. We convert into design wind pressure. That's very easy, half rho V squared, and that value. And then depending on the shape of the bridge element. If you go to bridge element, there are many different shapes. Like if you go to your bridge girder, if your cross beam, your collar pier, they all are different concrete shapes. They all have a different aerodynamic effects. So based on that one, you calculate the drag coefficient and other coefficient, and using those, you convert your design wind pressure into a design wind force. I'm not going to go into detail with those. And this design force, we can calculate three-dimensionally. It could be longitudinal. It could be the transverse. That's normally significant wind, because the bridges are longitudinally quite long, and you got a barrier. Your superstructure, the total depth sometimes is close to 3 to 4 meters. So in general, it's about 3 meters. So there's a massive horizontal force acting on your bridge superstructure laterally. So then again, the longitudinal direction and the wind sometime in the open area, you can see this picture itself can create the vertical lift as well. And some bridges, if you can't use this one, what we're going to do the wind tunnel test. Like, for example, if you design a cable stay bridge or suspension bridge, arch bridge, even some small bridges, we carry out wind tunnel tests to understand the bridge behavior and the shapes we use in the bridge. It's going to aerodynamic shapes is right, or right is the right sections we use for this bridge. Yeah. And then I'm not going to discuss those things in this presentation. And the wind force, I'm not going to spend so much of time because it's quite familiar with you. You know exactly how to calculate them. And then when we were calculating the wind pressure, it's I just used this one, the units Newton. Is the half rho is the density of air. We divide that one, you got a 0.6 VU time area time the coefficient, the aerodynamic coefficient, drag coefficient, and the lift coefficient. Those things you can, the Australian standard give you the figures to calculate in the same way. You use the Eurocode British standard, you can calculate them. And then for you to use, like if we use for a transverse wind, your bridge, when you calculate the transverse in the wind direction is the breadth, and your structural the depth D is D always the constant. But if you talk about the longitudinal wind, the wind direction is in the longitudinal direction, then your drag coefficient, calculate the ratio is based on the L over D, and that sort of thing. If you draw a picture like this, you can identify. I think this is based on the principle you learn about. I think the water is flowing around the cylinder in your fluid mechanics. The one common effect and the Reynolds numbers, those based on those things, the wind engineering theory is built on. Therefore, it's better you need to have an understanding, at least when you were using these codes, what is the direction of the wind. You need to go back to the old day, what you learned. This is the very common example everywhere. The flow through the cylinder, that's the circular shapes. Yeah, and that the same principle apply in here as well. Yeah, I'm not going to spend so much of time about wind design calculations, because every one of you know quite well about this one. Then I'm going to spend some time about the flood loading. I'm not going to ask you whether you have any question about the wind. I'm sure you all are quite good expert in wind calculation. You all saw this picture before, the flood loading. I'm going to spend some time about the flood loading. The one reason is I couldn't find proper detailing in the Euro standard as well, and the Australian standard, especially after 2011 flood in Queensland, when they were revised this Australian standard in 2017. I think the flood loading section has have a significant improvement, and it incorporates so many things. It's quite comprehensive as well. If you do not have a code to design the flood, I suggest you to refer to this code. And I put a lot of information in here. I'm not going to explain all of this information. You can read through that one. That's why you can see 76 slides in this presentation. Yeah. During the flood, you can see this, the top right-hand corner. During the flood, yeah, you can see this pier start tilting. And you can see at the bottom left-hand corner, during the flood, you can see debris and so many things in here, the water, and so many things is holding up in the bridge. And you can see on the top left-hand corner, after the flood, you can see these piers exposed, and these piers were exposed. And you can see on the bottom right-hand corner, yeah, the solution is very easy. You don't have to do anything. You have to go back and build a new bridge after flood. Yeah, right. So that's the impact of the flood. The flood design approach is a bit similar to the earthquake design approach. So the importance levels of the bridge play a vital role. Like a BEDC category Pro is required to perform after the earthquake is similar to, you will see, you can design your bridge to perform after massive flood. That means after the flood, there's cover and other things, they are still to perform that. We will see how we're going to design to that. And when there's a flood, you can see from this picture in here, all this pile, this rake pile, I think it's an old bridge, is all exposed in this river. You can see this river is quite long, right? When this pile all exposed, the lateral resistance provided by the soil will disappear, and we really don't know exactly what is underground as well. And then when the bridges always subjected to the massive longitudinal load, you saw that one in Euro code as large as 900 kilonewton, and in Australian standard as large as 1,200, and it will be multiplied by 1.8. You will see them later. So they're going to subject it to significantly large longitudinal load. Again, depend on the way the geotechnical engineers design the pile. If you have significant cover in your bridge, you will lose a lot of the capacities as well. You can see in this particular bridge, I just drew what is the ground look like after significant flood event. So it's all the pile exposed. So therefore, you can see in this picture, I have this the truck in there. I just show this, the braking load in the bridge. So that's going to affect, because like when you lose your cover depth, sometimes it's significantly large, it's maybe 7-8 meters, sometime in a river, the exposed length of the pile, if the already is 17 meters, if the cover is another 10 meter, it's becoming 27. So it's significantly large. That's the proportion. You can't compare that value only cover itself, how much the height of the pile within the river as well. Even it's not only the river, any situation is the same. So when the exposed pile reduce the capacity, so then the outcome would be like before, the bridge may need to replace, or else bridge may not be serviceable until you go and fix your cover. You go and fix this one. So go and backfill with the rock and thing, you reinstate that in area. So then in a major, the routes, bridge should be serviceable with a cover, because like we discussed in the earthquake design, the bridge earthquake design category 4, if it's a major, this bridge serve to economic centers, right? It's one of the main transport routes. So then you can't say it's affected by flood. You can't let your heavy vehicle in that road. Even if I reduce the speed to 10 kilometers per hour, still it's doubtful whether we can allow you to use this bridge. Because of that, it's very important you design your bridge for the flood loading. And important, you check your bridge after flood event, right? Because check your bridge after flood event, you can have your traffic, even with the control environment is decided by the traffic agency. You don't want to use 100 kilometers per hour normal day-to-day serviceable state. You can just tell, okay, we can let you use this particular bridge, but you can't drive 100 kilometers per hour. You just drive 40 kilometers per hour. Still, we can let you to use the bridge. You can have a controls, but still it should be usable. I got the opportunity to involve after 2011 flood in Queensland to go and work in the Queensland office when I was work at SMAC. I was able to look at some of the bridges damaged by flood, especially bridge superstructure, substructures, they are serviceable, but because of the significant cover, we can't, we recommend the client to, it's not serviceable at this stage, they have to replace the bridge. Yeah, we need to make sure that we are designing the bridge to that one. I'm explaining to you this thing, the earthquake and the flood design. Most of the bridge designs you do, it's not going to be the governing case. Most of the bridges is governed by the primary load case we design as the traffic, but you need to pay attention to when you design the bridge for the flood and the earthquake and this thing, because this thing you can't count them, you can estimate them. But if you properly design them, if the impact is worse than what you expected, but still you can use the bridge. Yeah, you don't want to close it. You don't want to replace in the worst case scenario. I think I explained this one in detail in my previous session. I put the same slides in here for you to understand. When we were designing the bridge loading, we need to have a two limit state condition, ultimate limit state and serviceability limit state. For the flood design, we use the serviceability limit state for, again, depend on the type of the bridge, where it's located, how important those bridges. But in general, I should say the 1 in 100 year. And for the ULS, the return period, or we call average recurrence interval, ARI is 1 in 2000 year, we call ultimate limit state. These are significantly large floods. And even a 1 in 100 year also significantly large flood. We say 1 in 100 year, you should not see that sort of flood in your lifetime. Yeah, and yeah, we designed. That's what I put include this slide. You have seen this one before, and you have seen this one again before. The flood design criteria, I put these values in here. So when you are designing for the flood, is the forces related with the flood. It's because of the hydrodynamic force, and with the debris, and sometimes the lot of logs or pontoon, or sometimes even houses come and impact your bridge. You need to take into account these forces, and the ship impact, especially in rivers. I think I discussed this one in the previous session. I'm not going to spend much the time in this presentation to discuss about the ship impact on bridges, but I more focus on the normal floods. And then when we were designing, we do flood modeling, and or else you can use the empirical formulas. We know the limit state, the SLS is 1 in 100 and ULS is 1 in 2000 year. Then you can instruct your drainage modelers to come up with the design parameters what you need. So you need the velocities, you need the cover depth, and then you need the flood levels. You need to know relatively where this flood levels in your bridge. And if you have those information, so then you can design your bridge for the flood loading. Yeah, the flood is quite similar to the wind. Yeah, the difference is the air and the water. but the cover depth is one of the important as the impact. If you do not have a flood modeling or flood loading with you to design a bridge, maybe I will find and put some guidelines. You can assume anything silty kind of a material is on the top will be flushed away with this kind of a flood event. There are some, I think the guidelines developed in US, you can do hand calculations before the software has come. People do hand calculations to calculate this cover depth. You can estimate that one. Even you can look at the borehole data. You can grab the borehole data. You can have a close look at that one, and you can get yourself an understanding. So you will learn at during the presentation when you go to the load combination. If you sometime estimate the cover depth and other thing, the loading little bit conservatively, still in terms of the design outcome, that doesn't make a significant difference. Yeah. Any questions up to here? No, then I will jump into this one. Okay. We need to calculate the force due to flood. Is the water flow. You see this one. There is a debris. Okay, we separate. First, we calculate what is the force due to water flow. Right. As we know, like air, when there is a massive flood, what happened in here? This picture, you can see this the bridge elevation, the cross section I have put in here. I have a yellow color right at the bottom. That's the pile. Is below the cover depth. I have this line as cover. Before the pile, normally up to the top of the footing, we fill with we protect from this cover, or else normally we put the foundation 1/2 meter below the ground level, at least 1/2 meter or 1 meter below the ground level. So this whole thing is gone. Even the section of the pile is exposed, right? You saw in these pictures, it could happen, right? It could happen in here. So then the section of the pile, this H2 is exposed because of the flood. And your footing is exposed because of the flood. And your column is exposed because of the flood. In this diagram, the flood is below the bridge superstructure level. This is the flood. This is not right exactly. Flood in ULS level should be higher than the SLS level, because the return period, we talk about one in 2000 year one. Because of that one, please correct yourself. ULS flood has to be a higher level, or else strike out or put a bracket in there. But I try to explain in here in the flood design. So you need to apply this flood force on your pile, on your exposed pile, section, exposed footing, exposed column. Like you design wind, exactly design like a wind, right? But you know, like the air, this is the bed, right? This covers the base level. In here, the velocity of water is quite less, it's quite higher when it's go up. Where the drainage designers give you this the speed of the velocity of the flood. They calculate this cross-sectional area of the river or creek or cross-sectional area, and they get the volume of water is going per second, and then they divide that one by the volume of water, the rate divided by the area. That's how they calculate this the speed sometime, or else they can give you the value on the top surface of the flood. It depends on the modeling. If you are really keen, you can apply all these forces in this level, but it's a bit too conservative. If you apply the velocity 2.3 to apply in the column as well as in the bottom section of the pile. Yeah, is a bit too conservative, but you can just make your judgment. You can see the bit of a understanding about the distribution of the velocity across, and then you can make estimate like a parabolic variation. So based on that, you can calculate. So the dynamic, the force, or the drag force, what we call the drag force, we call, before I get into that one, I just want to explain, same like before, like in the wind, because of the water, the flood force on a structure, it can exert three-dimensional force. The one is a longitudinal, we call is parallel to the traffic. The other one is transverse direction, is perpendicular to the traffic or your bridge structure, right? The other one is the lift, because of the water pressure. If it is under the water, you get uplift. So the one on the parallel to the direction of the water, we call the drag force. You can see in this diagram, because you can see we put the bridge across the rivers, not parallel to the rivers. That's why my traffic direction is perpendicular to the water flow, right? So normally you can see when you are building bridges, we always put our piers parallel to the water, because parallel to the direction of water, to make sure that the flood forces we can minimize. And again, this drag force is similar to the wind, is 0.5 V squared time the area, the pressure, time this CD, the factor. You need to calculate in terms of that. This 0.5 is always, this is in kilonewton, because density of water is the 1 ton per meter cube, or 10 cubic meters, 10 kilonewton per cubic meter. So then this factor times CD and V squared AD, this CD value, you can again, the drag coefficient is again, it's depend on the shape, right? So this streamline shapes, we always use, like in the aerofoil, we use that shapes. So that will reduce the drag force on your substructure. That's why when you are building bridges on creek and rivers, you have a not rectangular shape. You have it's difficult to build, but you have the streamlined shapes in the constructions. So you get the rectangular shape, the highest drag coefficient. So then if you know the drag coefficient, if you know the velocity, you know the area of the exposed area of the water pressure. So then you can calculate the flood force. Here, for your understanding, I have already calculated this area for you: column section, footing section, and the pile section. With the pile, you need to get the projected area, that's diameter times the height. I put a note in here: for accurate analysis, flood velocity profile along the depth should be considered. Yeah, this is exactly same as the way we calculate the wind. And the flood is always, it's not moving exactly parallel to the face of the parallel to the face of the column. It could be in an angle that could generate the forces in the other direction as well. So this is how we calculate the drag force. The force is parallel to the water flow. Any question here? Quite straightforward, this one, similar to the wind. Yeah. Then we calculate the force perpendicular to the force perpendicular to the wind, because you see this flood force is acting on the bridge in transverse direction, the drag force, but the side force will be acting perpendicular to the girder because of the water flow with an angle. and that load is on the longitudinal direction of the bridge. That is the direction of the traffic here. But you need to remember the area of the exposed area of the bridge is quite significantly large compared to the drag force. That's what I have this elevation. And then I have these areas I marked for you. Yeah. Again, this one is the 0.5 CS V squared AL. The area is the exposed area. That area is significantly large compared to the drag force area. The OAS 5100 has given this value is quite conservatively is 0.9 if the angle of this, the direction of the angle is less than 30 degrees. This is quite conservative, like if your water direction of the flow and this if you place your pier parallel to that one, is 0.9 value is a bit conservative, but you can use the appropriate value. I mean, if you design to Australian standard, you have to use 0.9. There's no argument that one, but if you use the other design standard, you can even reduce that one, because if the angle is 5 degrees, you don't want to use 0.9 when it is 30 degrees. 0.9, you can see it's greater than 0.9 is becoming 1. So any direction, like the water is coming right perpendicular to the force is like a drag force. Yeah. So please use wisely if you use these numbers. Yeah. Any questions? No. Then the lift on the structure. This is because if a bridge is underwater, right? We have a lift, right? We know it's a buoyancy force. Again, we have an uplift on the lift on the bridge. This calculation on the lift on the bridge, we have one is because if it is underwater, water is moving and is pushed against our superstructure, because superstructure got a depth. That depth we call DSS. These are the superstructure depth. SS means superstructure depth. Yeah, if you get normal super T bridges or high girder bridges, this depth is quite significant, so almost about 3 meters, right? That gives you this drag force 0.5 CdV squared area AS. AS is the length of the bridge, right? Depth AS is length of the bridge times the DS is length of the bridge times the depth of the superstructure DS. It's quite large force on your superstructure. And again, because when the water is flowing across in here, like because of this, the water is coming before bridge is just flow, like in the cross section. When you put the bridge, there's an obstruction in here that create wake underneath the bridge superstructure. This is quite complex. That generate different pressure distribution across the bridge. That cause the uplift on the bridge. That uplift you can calculate again. Is a pressure is related to V squared and time the modification factor. These factors, yeah, they derive with a lot of experiment, research, and yeah, these factors design. Because you have a horizontal force, you have a vertical force that create unbalanced movement in the bridge. It's a quite good example in here. Some bridges, this one is not underwater, some bridges still because of this unbalanced force in here. Create the moment, that moment again add more to the uplift and more to the downward force as well, right? We know that downward force is not going to govern in the bridge design because we designed the bridge for traffic load. But this uplift is quite critical. Because of this uplift, sometimes your bridge might dislodge, separate from the bearing. With the horizontal force, it's move away. Because of that, your bridge may be dislodged. So it's very important you to design your bridge for this force. And the way it's calculated is based on the hydrodynamics. It's very important for us to understand what is the bed level to the these parameters they define. When you calculate this CD, CL, CM, to convert this pressure into a force, you need to calculate these parameters. These parameters is depend on, like you all study Reynolds number, Froude number. I think the related to that one. The numbers depend on the ratio, about the depth of the water from the soffit of the superstructure to the flood level, right? TWG to the depth of the superstructure depth, total depth of the superstructure. If the water is above the superstructure level, so then this value is greater than 1. If it is under the flood level is under the superstructure level, partially submerged, then this value will be less than 1. And the other factor is the ratio of the depth to the water depth to the superstructure against the depth of the superstructure. These are the parameters. So you gird, the deeper the girder and the shallow the girder, like a plank bridge, an eye girder bridge for 20 meter, 30 meter, you got a different superstructure depth, right? Then this is the code given you, the definition of this one. This one, I put this one is fully submerged and partially submerged. They define the partially submerged one because the water level is below the top of the barrier. You know, the bridge, we have a barrier going on either side. So it's just below that one. And the definition exactly the same. The water level to the DSP, they define. What happened in here, if the partially submerged one, the depth from soffit of the girder to the top level of the bridge, and the DSP used in the calculation is exactly the same. And then yeah, you can use these pictures to differentiate when you calculate parameters for fully submerged or partially submerged bridge to analyze. And using those parameters, you can calculate the drag coefficients. I put in here the partially submerged one and the fully submerged one. Depending on the parameters, the drag coefficient is getting increased. You can get a bit of understanding in here. This PR. This PR value, the superstructure depth to the depth of the water below the superstructure. You can see deeper this height, deeper the water depth, right? Lesser the CD factor. And shallow the water depth, this factor is becoming high. It's go up to like 3.2, right? I'm not going to explain this hydrodynamics. You just go back to your old fluid mechanics note and get some feeling about it. Yeah. And these values, they said you can interpolate between linear interpolation. So these parameters easily you can calculate using this SR and PR, submergence and proximity ratio, these parameters. You can calculate the CD value. You can calculate the CL value for lift, and you can calculate CM for moment, right? So if you know these 3 forces, you know the lift, you know the horizontal drag, you know the moment. That moment, if you know the moment, you can convert this one into couple, and then you can get the total upward force lift on the bridge and the downward force that is not critical in the bridge, then you can check whether your bridge, if it is a lift force is higher than your self weight of the bridge, you need to include the buoyancy as well. You need to understand, in addition to that, the buoyancy force is there. If it is higher, so then you need to provide the vertical restraint to hold down the bridge. Vertical restraint to hold down the bridge. We discussed this one under the articulation. I will put a slide to discuss about how to hold down the bridge. Yeah. Someone says it's easy. You put the post PT bar in here, attach that one to the bridge deck, and yeah, put a nut in there. It will hold the bridge down. Yeah, you can do that one. But remember, when you were putting all this restraint system, you need to make sure that the bridge is moving in and out all the time. You need to make sure that you allow that one. Yeah. Is it clear to you how about the flood loading on the bridge? Any questions here? Because the next slides, I have a couple of slides about flood loading. I'm not going to explain them because these slides all about explaining about a lot of descriptions about those parameters and other information in the code. Any questions? Okay. Yeah, these are the description about more detail. Before we calculate because of the water flow, the pressure loads on the flood. The other one is this one, the debris. So the debris also we need to calculate the flood load. This is very hard to quantify that one. Again, the code define this one as similar to the water pressure. Yeah. The only thing you need to, yeah, because this is the like, how to explain this, the picture in here, how do you going to convert that one into a pressure for us to, for bridge engineers, for us to design, yeah, simplify that phase is convert into the water pressure. That pressure, the velocity is exactly same as what we use get from for the ULS and SLS, one in 2000 year ARI and one in 100 year ARI. So the important is the area of the debris mat we're going to calculate in here. The area, they calculate the length and the depth. The depth can vary from 1.2 to 3 meters, depending on your superstructure. And like, if you have a shallow superstructure, you don't want to use 3 meters. But if your superstructure depth, let's say sometime you can have a superstructure depth across the river, even like a Penang Harbour Bridge is as deep as 12.5 meters. So then it's okay to assume this depth of the debris is equivalent to 3 meter high water pressure. Yeah. And they said when you were considering the length, the maximum is 20, or else the average span between the length, because when you design the bridge span, some span may be like 10, 12 meters continuous span bridges. So in that case, because you have a pierce in every 12 meters, you don't want to consider 20, then you average span that is less than 20. So you can get the area of the debris. Then if you know efficient, again, you can apply this force. They said you apply this force, a debris acting on a superstructure shall be considered for bridge where the flood level is 0.6 meters below the soffit level. Yeah, if it is a fully submerged, it's not required to use that one, but because if the water is under, because that's where it makes sense, the debris will come and trap with the bridge superstructure. But there are the cases, if you see the recent flood, even if it is underwater, still a lot of debris trapped inside the bridge sometime. Yeah. And anyway, the code defined that way. So yeah, it's make a lot of sense, and we can use that one. And the CD is again is a function of the fluid number, is the V over G Y. I think the Y is the depth of the water, and then with these parameters you can calculate the drag coefficient for superstructures and pier, and then you can calculate the debris loading acting on superstructure and substructure. Any questions? No? Then the other one is this new thing it's a log impact. Makes sense, right? You show during the flood, not the debris, a massive, the structures is floating and come and hit bridge. So sometimes there were houses, sometimes like especially in Australia, like boats and pontoons, and sometimes some people do a lot of timber related industries close to the rivers. A lot of logs come and come and hit. You don't believe, I think there were incident, there were incident that massive rock, significantly large rock moving with the water and hit the structures. So the courts say to get the log impact, because they said assume the 2 ton weight is quite significantly large. 2 ton is equal to quite a large vehicle weight, and impact from that weight you can apply, because what you can assume, this one is similar to the impact. You have let's say the 2 ton weight log is moving with the water. It's got a momentum is equal to the speed of that object is equal to the speed of the flood. It's safe to assume that one. So then that momentum and kinetic energy in that object is the mass time the velocity. The velocity you can calculate corresponding to the flood event. So when you get that one, if it is a hit on the structure, so that structure could be a timber, it could be a hollow concrete pier, it could be a solid concrete piers. If it is a hit on your superstructure, the reason this one they got the rigidity of the structure. Because of the rigidity of the structure, they said the energy dissipation approach you can use different way. If it's timber, it's more flexible. With the concrete, if you go to concrete hollow, is more rigid. But if you go to solid concrete, it's rigid than the hollow concrete section. It's more rigid. That means it said if it is a hit, it's going to move only 75 millimeter. I think I use a bit of a maths and I calculate this one. I prepare for you this equation, log impact force is equal to V squared over S. Yeah. Because I convert this, the force is kilonewton. 20 ton, I think should be V squared over the half mv squared. Half mv squared is equal to the F time D. Or else you can get the acceleration is equal, V squared is equals, acceleration is equal V squared over 2A. Because when it's, this is the analogy I use in here, the object is moving a distance S with the velocity V. So then the V squared, the initial velocity is V, is there, the final velocity is 0, because it's the impact means decelerate, then your deceleration is the A, then V squared is equal, or V squared 0, U squared minus 2A is equal to 0, then A is equal the V squared over 2S. Then if you multiply that one from the mass, then you can get the your log force in here. Yeah, the S is in meters, so you can calculate that one. using that, you can get the log impact force. This force is quite significantly large because significantly large force because of the 2 ton in here, the 2 ton force. Another thing, the code say the impact and the buoyancy from the large pontoon items and such as pontoon craft shipping containers shall be considered separately. If you has to design for those things, you have to look at them separately. Any questions up to here? If not, I think the flood design section is already covered. Then I'm going to touch base with the differential settlement. I think this is the quite obvious one. A differential settlement we got along the longitudinal section of the bridge because of the bridge loading, because of the different ground profile. You always have a differential settlement in the bridge. If you have a differential settlement, you can see this picture. The bridge will tilt. It will induce a lot of forces. It will affect your bearing designs, the bridge articulation. It's got a lot of impact. I'm not going to discuss about the subsidence effect. In the mining areas, if you build a bridge, you have to get the subsidence effect. That affect the mine subsidence effect on the ground is significantly large to compare to differential settlement. The differential settlement in the bridge, if you just look at the geotechnical engineer's settlement calculation or your own settlement calculation, you will see the differential settlement between 2 bridge piers is not go more than 10 to 15 millimeters. If it is a large span bridge, long span bridge, it may have a little bit different, but in general, it's not that significant. And the effect is the additional force on the bridge articulation and the performance of the bridge, especially if it is a differential settlement. Sometimes a bridge barrier, railing and other thing deform. If it is significantly large, it's going to impact your bridge performance, appearance, and so many things might crack. The solutions include, you can apply in your bridge model predetermined differential settlement. The 20 is quite reasonable. It's conservative as well, or else you can do the 3D bridge model. We always do soil structure interaction model, and the behavior of the ground over the years. And this thing you need to have a better understanding before you put that one, or you can incorporate in different way with your soil structure interaction, like an iterative approach. It's all depend on how important that these numbers are, but in the normal ordinary bridge, short span bridges, it's not that significant. And the subsidence effects, because we're not going to discuss this one because that's a very specialized area. You need to consult a specialist to get that advice, how much subsidence effect, and the you need to include in your bridge design. Yeah, because that bridge articulation and the design looks totally different to the normal bridge design. Maybe in the articulation session, I will show you one example in the mine subsidence area. When we design a bridge, how we're going to articulate that one to incorporate that the movement in the ground. Yeah, the bridge we can articulate to incorporate a lot of movement in the ground. We can come up with the special bridge structures. I will show it to you then. Yeah, and you can see this is one of the 3D the bridge model. You can see this pile be replaced with the beam and the set of linear spring, and then your footing and your column, your bridge superstructure. We model everything, and in this one we consult with the geotechnical engineers. We use the proper springs, and then that incorporate the bridge deformations incorporate in here. But if you need we can incorporate predetermined deformation in the bridge, 20 millimeter, and we can check the deformation of the bridge. If you're designing a continuous span bridge, that is quite important, the differential settlement analysis, because if this particular bridge pier settle by more than 20 mm compared to other two, that generate the significant the bendings and the forces in your the spans because of the continuity in the bridge deck and the superstructure and the substructure. It's all depend on the type of bridge to bridge, how we're going to employ them. Any questions in here? No. Then I put as for the completion of this presentation, I put the bridge barrier design. I discussed this one with you all in detail during the session number 2. I incorporate those slides, but I simply modify them. You know why we need bridge barriers. This impact forces on the bridge need to be, we need to design to contain. And again, you could see the aftermath if we not properly design them. And then how we're going to select them. We discussed this risk-based approach. And the only thing, but I did this in presentation slides, I incorporate additional information for you to, if you need to do a risk assessment by yourself. Of course, the bridges we design for the traffic, and then the risk is always based on the traffic volume. Higher the traffic, higher the risk, higher the heavy vehicle, higher the risk. So then we discuss about the road types and the road gradients. If you go uphill, the risk is less, but if you go downhill, it's higher. So there's numbers how you're going to get if the gradient, if you are going on a straight gradient, to drive out of the way is less, but if you are driving on a curve, you know now there's a significantly large horizontal force push your structure away, that increase the risk. Another thing, the deck height, if it is a fell down, what is the underground, the properties, how is going to impact the people lives, what is the risk associated that one. So it's all risk elements, and then from that one we can when we can compare that one against the actual bridge, the bridge what we got when we design the bridge. When we design every vehicle, we have a nominated speed on that particular highway. For example, most of the highways we design for 100 kilometers per hour, or at least 90 kilometers per hour. Normal roads we design for 60 kilometers per hour. The vehicle speed is important, and the shoulder width, the higher the shoulder width, there is a time for driver to react to that one. And the percentage of a heavy vehicle, that means higher the number of heavy vehicle, if it is impact on the bridge barrier, that's the higher the vehicle, momentum in the vehicle is higher, then the risk is higher. This whole thing is correlated. And then, as I mentioned, everything we correlated them together, convert into a average annual daily traffic per day to this factor. The what we use in our normal traffic modeling, that value we magnify that one using these factors, and how the correlation between the factors. For example, if it is the one-way traffic, right? It's only your factor is higher. If it's a two-way divided traffic, you see the number of lanes, 2 or more, is the one. But if it is a two-way undivided traffic, because there is a risk that you just go and hit higher the risk, so that the factor is becoming 1.5. Again, in here, the curvature, you see if the bridge is a straight line, the curvature is almost infinity. Higher the curvature, the bridge horizontal curvature, then the risk is less. They're set to the 1. But if your bridge curvature is if your bridge horizontal curvature is less than 300, your factors go up to 3. So your average daily traffic is one value, but you have to, when you consider the risk, you have to increase that one by 300% or 3 times. And then that vehicle of the structure, the drop height, it's also related, that one, depending on the high occupancy to the low occupancy, and then the drop height, how many meters. So then the higher the occupancy down, you can see even your drop height doesn't matter 2 meters. The bridge, the shallow stage as well. If the consequence is very high, you need to use the higher factors. If the drop height is the higher, then this factor is going to increase as large as like a 2.9. So that's all increase your risk profile. And then the code give you guidelines. It's all depend on the different countries use different approaches. The way the Australian standard get this one, they define the number of heavy vehicles or commercial vehicles based on this composition: cars, trucks, and then the small lorries and the big articulated vehicle. There are numbers according to them. They get the composition. You don't want to, if you want get more understanding, you can get this slide and go to your friend who do the traffic engineering and sit with him. He can explain you more. And or else if you talk to them, they will give you the advice in this particular highway, this particular road composition today, tomorrow, and 30 years time. What is the commercial vehicle percentage we expected in our traffic modeling? So please note that you design your bridge for 100 years. So you need to use the 30-year at least prediction in your selection. So when you get those 3 values, the codes give you a graph, the monograph. This is, they have a different graphs for different speeds. I pick one for vehicle speed, 100 kilometers per hour one. This is common in the motorways in Australia. And then the average annual daily traffic is in the 10,000 times. The 1,000 times this graph, 1,000, 10,000, 100,000, and 1 million. And then you can see if your commercial vehicle rate is higher, that means the number of heavy vehicle in the bridge is quite a lot. For example, like if you are building a bridge very close to a port, that you hardly get cars, you get mostly the truck, and you will be somewhere in the 40% rate in here. You can see it doesn't matter low number of vehicles in here, your performance level in the bridge is higher. As I mentioned before, higher the performance level, the low is the lowest one we use in the bridge, the regular, and the medium is the standard one we use in the bridge design. You could remember in the first lecture I explained this is equal to TL5 crash load test, equivalent to that one. So the higher the impact load you need to design in your bridge. So if you want, you can just in your one of the bridge you design or you work on, you can gather this information. You can just do your own calc and you can see the performance level, what you need to design for your bridge and what sort of barrier you have in your bridge. You can just see the risk associated with that one. Or else the existing bridges, if you just want to evaluate, like a local areas in most of the countries becoming urban areas, on those areas, how we're going to evaluate them. And then as I mentioned before, the codes give you how to design this, the medium performance barrier. The impact load is the force we apply to design. This one in here, the horizontal force, the barrier need to design is 600 kilonewton. Yeah, that you can see the lateral restraint we talk about, we need minimum 500 kilonewton when you apply for every pier. So in a one span, if you put the minimum 500 lateral restraint, you get a 1,000 kilonewton minimum lateral restraint. So that 1,000 kilonewton would be able to absorb any truck hitting in your barrier that will hold your superstructure in position without letting that one to move. You can see why we need them. It's very important. Then your truck maybe hit the bridge, it crashed through the girder, it might fell down, but your bridge superstructure will stay in position here. And you can see if you use the low performance barrier, this is the lowest one, it's 150. I think the application of the load, the performance level is higher because this, if you just look at this mesh test data, you need to have the higher barrier as well. Yeah, not going to go so much detail into that one. Any questions? If you can ask one or two questions, I can clarify if you need more clarification or need to elaborate more in here. If not, so I will jump into the collision protection. Again, I think we discussed this one in detail, why we need collision protections. The highway structure, there is a possibility that one of these incident could happen. Yeah, one of this incident could happen. Any bridge anywhere in the world. So the consequences are dire because it's economically and safety wise, it's really significant. Because of that, we need to make sure we design them. And then I'm not going to discuss about the ship impact one. Then in the Australian standard, if you are building something close to a road traffic, you need to design for 2,700 kilonewton road. It need to be applied 1.2 meters above the ground. So you need to apply that force 1.2 meters above the ground in this level. That generates significantly large force on your substructure, as well as is translate into your superstructure as well. Again, when you put the lateral restraint block, it will help you to distribute this load. It will control the movement of the substructure. Yeah, and I discussed this one in the session 2 in detail. Different type of substructures we design, like a blade piers. If you go to the railway, that number is quite significantly large. You know, the rail bridges have a higher momentum than the vehicles. Rails has a higher momentum. The trains have a larger momentum than the trucks. So again, I put the same note in here for the ship impact. I'm not going to go this one in detail because we discussed that one in detail before. I just put this slide based on the Euro code. You can see the Euro code. If you have your piers close to your highway, you can see this truck is coming, is going. If we go over the road and it can go and hit any of these substructures, then that force they categorize based on the type of motorway. If this road is your motorways, then that impact load is 1,000 kilonewton. And then in the X is the direction of the traffic. Direction of the traffic 1,000. Perpendicular to traffic is 500. If it is in country area, is going down. So these numbers are specified in the Euro standard. The two code have a significant different extent in these numbers, but either code, when we were using it, you can do a risk assessment, and based on that one, you can decide which number to use in the designs. Yeah. Please note that if you are designing over bridge in a highway, across the highway, it's quite common when you are building highways and motorways, you need to design that one. If you haven't, you can go back and build rigid traffic barriers in front to deflect this errant vehicle crashing before it crashing onto the bridge substructure. Please note that. So it's related to the not only the people, the life and safety, and the bridge superstructure itself. Another thing is related to the legal aspects as well, like insurance and other things here. Yeah, I think that is the end of the session for the loads. I spent almost up to now close to 6.5 hours explaining the loads on a bridge. About close to 70, 80 slides. I explain the loads on the bridge. The next 2 slides is a very simple and straightforward. I will finish quickly. Now it's more than 3 hours as well. And up to now, do you have any questions? Still you can go back and read through these slides. If you have any questions, you can send me an email or ask before we start next section next week. I will still explain it to you. If you want to design a bridge, until now, what I explained to you, you need to have a better, you need to have a understanding. The people most of the time use the design is getting information from one place, putting that one into now modern day Excel sheet, and then compare that one, grabbing some information and put into another Excel sheet and compare these two. And then comparing those two numbers, they do so many manipulation inside by numbers. It's not. When you design a bridge, you're taking a massive risk. You are designing a structure spending hundreds of millions of dollars, and you are putting a lot of people life on a risk because people are driving hundreds of thousands of people use that one daily basis or yearly basis. So because of that, there are some minor detail you think is not important, like you will see this one, the next session when I will explain it to you, bridge articulation. How do you need to detail the bridge to accommodate, it can absorb all this loading, all these deformations. But before that, you need to have a really good understanding about what are those elements. You could see now in the bridge, the loads are extremely high. The structures are, the dimensions are really big. They are in massive. The bridges, they build now as long as 2 kilometers in the world, right? So you build the bridges to span as short as 6 meters, right? But you apply the loading system on the bridge, you could see none of these load we calculate, we talk about, you can't estimate. Even the density of the material, what we assume in the bridge design, we also guesstimate that. There's a variability on those things as well. In the load combination element, we're going to discuss that one. Because of that, you have to work with an open mind. That's what I need to say. Use an open mind when you design a bridge. Yeah. Someone can't force you to assume things, but you can do that one. You need to always make your judgment with you need to follow the design standard always that guide you. As another thing is a legal requirement as an engineer to follow the design code. And unless otherwise you come up with the solution is agreed by all parties, and then that is okay to use it. And you can use your experience, though we have a lot of experience on our own. We make judgment, we make certain things, but we can't bypass the design codes and things. So I want you to go back and revisit what I explained it to you up to now. Yeah, because if you need me to clarify anything, it's better to, I will spend some time beginning of the next session. If you have any questions, I can ask that questions. I can answer to you. There's a question about, could you please give me a brief idea about restraint moments built in bridge superstructure and the substructure due to creep shrinkage? I think the restraint moment on the bridge structures, the bridge structures is built up in the bridge structures because of the creep shrinkage, because especially in the continuous span bridges, because you build the bridges with the stages, right? And if a bridge is continuous span, just assume creep and shrinkage is the longitudinal, strain is longitudinal. It creates you axial force in the bridge. If you apply additional axial force, you replace the creep shrinkage with an additional force, axial force on your bridge. That will produce depend on the bridge articulation or substructure, superstructure connection. It generate a different moment in the bridge. Another thing, please remember that the bridge superstructures, when we build, like for example the I-girder bridges, or even to say the continuous span box girder bridges, sometimes we cast in stages that create the complex creep and a strain system in the bridge that create additional moment. We can do the analysis using the softwares like the bridge. You can see in this bridge, for example, the industrial ring road bridge, the one in my background. Yeah, that's bridge. When we designing that, the creep shrinkage to give you a significant impact on the forces on the bridge. Yeah. I'm not sure I explained it to you, that question. Did I explain? Oh, okay, then I will jump onto then the load combination one. Okay. Now we started when we talk about the load, we started with what is load effect. We categorize them: permanent effect, transient effect, thermal effect. I think even if you use the Euro code, any other code around the world, the concept is exactly the same. And then these effects we convert into what we call serviceability limit state and the ultimate limit state condition using the load factors. And then these load effect, then we combine appropriately to design the bridge. Yeah. I put this one in big. If it is a construction loads, bridge to bridge, the way we build, the way we construct is different. We have to do a special analysis for this particular bridge. So you can't apply the same like we're designing a bridge for that same standard. That is the beyond the standard. You need to do analysis, especially like if there's the construction stage in analysis is creep shrinkage effect is significantly impact the bridge behavior and the forces. We need to calculate them. Then if you know the load combination, so then we can calculate the actions on the bridge or the forces on the bridge. We call basically serviceability limit state, bending moment, shear force, and the axial force in any members or torsion. And then, yeah, bending, shear, axial, torsion. If you know that one, you can design your bridge structures. You can detail in a proper way. Then the same picture I included you before. The permanent effect, we have a load group. Transient effect, we have a load group. Permanent effect, that is going to be there in the bridge. And thermal effect. I need to mention again, the transient effect, the bridge we are designing for traffic load. The traffic load in the Australian standard, you need to magnify by the dynamic load allowance. But in the Euro code, it's already incorporated except some situations like in the fatty. Yeah. In the Euro code, to my gut feeling is the LM1 is the most common and governing load case. maybe LM2. So they all included dynamic load allowance. To converse in Australian standard, the load factors, I put them within bracket. For the dead load, we don't change it. For the superimposed dead load, we multiply by 1.3. The reason is we increase 30% the uncertainty, because the asphalt, for example, in the bridge, you put it there, but you have to overlay after certain years. Sometimes originally you say you have a 50 mm or 75 mm, 80 mm asphalt on the top. So when it's wearing off, the bridge deform, and then you come back and overlay again to make the surface smooth. So yeah, your thickness may be someplace 120, someplace 50 is uneven. Yeah, because there's a risk, and to take that one into account, they increase by 1.3. And when you go the serviceability limit state, like a water force, like a buoyancy, those things you need to calculate based on your recurrence interval. ARI is 1 in 100 year interval. But when you go to transient effect, of course, these loads, but I strike out minimum restraint, collision, impact, and earthquake. The reason I strike them out, these load condition we considered at ultimate limit state. Yeah. The thermal effect, the variation in the bridge temperature, that is a quite common one we use in the bridge design. The load factor is 1. We use the differential temperature variation that's specified by the authorities, but the Australian standard also, you can have those values, especially when we were designing the continuous span bridge and a special kind of a bridge. We use this one. Yeah, this is the this one. If you use the Euro code, you get your load classified like that, the traffic load and the thing, and then you have your these effects identify, then combine them together. Again, I just need to mention the wind load in here, the water flow in here. Water flow is 1 in 100 year ARI, and the wind is 1 in 20. Yeah, in the serviceability limit state. The construction load also, you need to do it separately, because during construction stage, you need to carry out serviceability checks. Otherwise, sometime construction stage, the bridge tend to crack if you not properly detail it, and if you not properly check that one. Then the ultimate limit state combinations. This is again based on the Australian standard. And you can see the dead load, you multiply by 1.2. So superimpose dead load by 2. The dead load by 20% by superimposed dead load also, like asphalt we put, is like permanent effect in there, but the risk is higher. The code say you need to multiply this one by 2. And the earth pressure by 1.5, the creep and shrinkage effect by 1.25, the differential movement 1.5. In the buoyancy, we consider ultimate limit state event as a 1 in a 2000 year event. You can see in the dead load and superimposed dead load, I have another 2 numbers, 0.85 and 0.7. Why we have these numbers in here? For example, when you were checking your bridge and your pile for uplift and tension, right? You need to consider the, like I mentioned before, your density, what you are assuming. For example, the reinforced concrete element, 25 kilonewton per meter cube, and your asphalt 22 kilonewton per meter cube, your density of soil 18 or 20 kilonewton per meter cube. There may be a variation in this thing, right? Because of that, this code say you use the lower value. There may be that variability in your calculation, and because of that, your estimation you use in the weight assessment, you reduce, that generate the stability, the side when we looked at in the structure shape approach. Like for example, if you reduce these values in the bridge, and if you take a pile, sometimes the pile maybe go under compression with 1.2 and 2 dead load condition, but if you use 0.85 and 0.7, it may be under tension. So then you need to go back and check your pile can take that tension in the pile, and your bearing, with the bearing will have an uplift. So the design code need for you to look at this thing. And then you go to the transient one. Of course, you can see in the Australian standard, the traffic one is multiplied by 1.8. I put in here, this need to be increased by the dynamic load allowance. But the traffic load in the sense is include, please note in the Australian standard, is include braking and braking and centrifugal force. As I mentioned before, minimum restraint, collision, impact, earthquake, they all be considered as ultimate limit state events in the bridge design. So that's why these factors are 1. And the water flow and wind, we consider 1 in 2000 year RI. Yeah. The variation in the bridge temperature, we use 1.25. Yeah. These are the loads. Yeah. That's what I warn you to use the same thing. For example, in the traffic load in Euro code, you multiply by 1.35. The characteristic load model LM1 to LM4 defined in that one is in general multiply by 1.35. Don't compare the codes, but this is the approach used in the Australian standard. Yeah. So now you convert your load SLS, you convert your load to ULS. Now, I will say the language you all understand in Sri Lankan context, like I'm going to make a fruit salad now. I prepare all my ingredients here and there. I'm going to mix them. You see, I'm going to mix it in the right way to get the right taste, right? Let's see in the next slide. This is my load combination. It's the same. You saw this slides over and over again. I have my permanent bridge traffic loading, the pedestrian and maintenance site loading, minimum restraint one, collision load, impact on barriers, earth pressure that is on the back of the bridge, earthquake load, water flow load, wind and thermal. Yeah. If you go to Eurocode, you got exactly the same thing. You got exactly the same load kit. You trust me, there's no difference. And you got exactly the same load codes, but in the Eurocode, what the code does is compare the occurrence of this loading. Yeah, they categorize again this load into two different space, two different categories, right? We designed the bridge for traffic load, therefore its permanent effect is there. The traffic load effect is there. In this LULS combination, I connect A and B together. This is what we design, right? The code says it's better to you check the A and B, the permanent and traffic together, because the temperature variation is all the happening, seasonal changes is go up and down. Use the temperature effect, the thermal effect, the K, but use the serviceability limit state condition, not the ultimate one. So while the bridges we are moving, the traffic is, the wind is there all the time, it's affect the bridge. Give it a try with the horizontal forces due to the traffic load, but this condition is a special one they call 35 meters per second, that's still 100 kilometers per hour. That's not quite uncommon in Australia, and this wind. And you use this wind apply on your structure. So this is the load case one I categorize. This is the one when you design a bridge is always covered. It's always covered. Then A plus C, okay, with the maintenance, if you have a pedestrian cyclist, okay, you add them together. And A and D, of course, you have to design your bridge for minimum restraint, like for example, upflip and hitting something. So you need to restrain your bridge 2% of your dead load, or at least 5% of your 500 kilonewton. You just need to do that one. And A plus E, because of course the bridge can be subjected to collision. Yeah, the bridge can be subjected to collision. Again, the set. Now, AE plus B. B is traffic. Okay. Your bridge is subjected to collision, but you have to design for traffic load with SLS traffic load. Okay. I have a note 2 in here. Bridge should be designed. This should be serviceable after collision on the substructure. Before I go into more, I will go to next slide and I will show you why. You see, this is the highway. We build this. This is your motorway. Or this is the road. This is your pier here, right? This is your motorway. It's on the top, right? If a substructure is collided, the structure, the vehicle collided with the substructure here, right? If this bridge is not serviceable, right? Like if you want this bridge to be serviceable, because you want to open this the motorway all the time, so that make sure that you let at least the engineers go and inspect the bridge and the retrofit in the substructure is okay, but you need to make sure that you design your bridge to the traffic load, not the ultimate limit state one. You could see the ultimate limit state condition is 80% higher than the SLS loading. So you need to design your bridge for, you need to check your bridge for that load case. Yeah, that's what we combine them together. Then A plus F, yeah. When there is an impact on the traffic barrier, quite obvious. We design mainly the traffic barrier for that force. We know our substructure can absorb that load, but sometimes if a short span bridges with, if an impact load is in here, if you're not properly restrained, your bearing may not be able to absorb that load. Because of that, you need to make sure that you have a proper restraint system to allow that bridge is not going to move. So A plus F. And the other one is A plus G, the earth pressure, that is we going to, when we check the bridge abutment, we get that combination. And then the other one is A plus H. Yeah, of course, we had to design the bridge for earthquake as well. Bridge for earthquake loading as well. And the previous approach, we make sure that we consider our bridge design. The approach we use in our bridge design, we say if this bridge required to be serviceable, we're going to go in a high level of analysis, and we're going to go with a very high level of detailing. That's maybe the reason the code doesn't use this one, A plus G plus the SLS traffic. I'm not sure I missed that one or not, but anyway, we design and detail this one for, if I missed that one, next week I will explain it to you. Permanent effect and earthquake effect on the bridge. But you will see if it is a bridge category 4 or 3, when we come to detailing, it's go to a long extent to make sure that bridge is not going to crack, or bridge is serviceable. It can be used even after earthquake. And the other one is the A plus I is with the water. Again, with the water flow, during the water, this is the, please understand, we need to design our bridge during the flood event to resist that force that we discussed, the flood load. But after the flood, we need to make sure that bridges are still serviceable, A plus I plus B, right? The B will still be used, not the ultimate traffic load. We use the serviceability limit set traffic load. The reason is, after the earthquake, your bridges cover like this. Your column, the pile exposed, your substructure is different now, not like before, but still you should be able to have a truck on top of the bridge. But this one can nominate by the road agencies, like you can have a controlled environment in a particular case. But with my experience, I think this load case is still, it's not governed in the bridge design. And then the A plus J, you design this one with the wind. But you see, in the LC1B, we look at the case, the loading with the wind, traffic and the wind together. The other one with the thermal effect only. Again, we looked at the traffic with the thermal. The codes say we do vice versa as well. Ultimate thermal condition with the SLS thermal loading, because some bridges, like a continuous span bridges, sometime when you design these load cases is governed in a special occasions. Yeah, this slides, I explain it to you again. Then if you go to the SLS stage, you can see the D, E, F, H. These are ultimate conditions. We just strike them out. When we were designing permanent condition, of course, again, the codes say when you combine the permanent load together, you can combine the permanent effect and the transient effects and the thermal effect. You can mix together, and the permanent effect and the transient effect, always we design bridges for traffic. And you can combine with the thermal effect. And you can combine the traffic, permanent effect and traffic with two transient effect, thermal and the wind. But you have to use different factors. And then we can generate the combinations like that. There are not so many combinations. When you design the most of the bridges, the combination 1 and 2, most of the time is governed. It doesn't matter what code you use in the design. And then I didn't just the touch base with the one slide I have for Eurocode. Eurocode, as I mentioned, the Eurocode got the load effects is based on the characteristics values and the frequent value. I'm talking about live load in here. The frequent effect, the way they say the frequent is like this loading system is quite commonly used in the bridges, like a once in a week. And they compare the characteristic value is a 1 in 1,000 year effect. There's a correlations they have developed between these two effects. Correlation is based on the effect to 1 in 20 weeks one. Using the simple maths, T is for week, T is for 1,000 here because it's a log in a logarithmic scale. You can get the relationship between 1 in 1,000 year and a once in a week. This is the like a characteristic once against the frequent one is about 60% of that value. The reason why I put these slides in here, because you can see when you go to Eurocode, Eurocode have the one table for frequent values. That one they combine like with the 0.75, 0.6, and that sort of combination in the I'm not expert in the Eurocode, but just the what I got in here. This the frequent and the these effects, they consider the characteristic and frequent effect in the bridge design. They want to incorporate them. They want to look at, they want designer to look at in different ways. But the I will study this one in detail, not now after these sessions, and I will explain you when I write about this small booklet about this one, how we're going to incorporate in a proper way. And then the Eurocode exactly same as the Australian standard as well. Your live loads, the LM1, that's the tandem one, and the UDL one, and the LM2, the axle one, and then the LM3, the special loads, that HLP load or heavy vehicle loads, and the LM4 is in the bridge design, it's not going to ground the crowd load here, and the braking and the centrifugal. And the difference in the Australian standard, the braking and centrifugal always go with the traffic load LM1, but in this one they got a clause. They said you can use that one if road agency in that particular country advise. Otherwise, they combine with the frequent load. I think using the table, Eurocode develop different load combinations. These combinations are not much different to the Australian standard, but I haven't used that code up to that extent to go and explain it to you in detail, and because I haven't even studied that one, because based on the Eurocode, with my experience in the other codes, I can tell you up to now, but the concepts in the design, the way we built up, it doesn't matter what design code we're going to use, it's exactly the same. Yeah. This is the end of the presentation about the last these two sessions. We spent more than close to 7 hours about loading on the bridge. I hope I just give you at least some idea when you are designing a bridge, what sort of loading you need to combine, how they were going to interact with each other, how we're going to estimate those load values. Yeah, and then even for example, in the Australian standard is quite good. They were explained in a one design, one volume. It's AS5100 part 2 we call the loads. But if you are using a Eurocode or British standard, so no British standard now, of course, now it's Eurocode. If you're going to use the Eurocode, that one you have to use the couple of different volumes to extract the forces. But still, I think like what you can do, because you can combine them together and you can create your own design volumes, and you can create your own nodes, and you can create this you can identify these load types, and because the transient effect is there, because it's come and go and thermal effect, and then these things you can categorize the scenarios. When you say traffic, it can be many different traffic. We knew all the code, any codes have a different traffic models to design, and then you can combine them according to the guidelines given in the code. All right, then anyone has any questions, any comments? Any questions or any comments? Is it clear to you all what I explained today? Can someone respond to me? Okay, if there's no questions, can you all hear me? Yeah.
Yes, we can hear you.
Yes,
Yeah.
sir, we can
So,
hear.
it looks like it's all good. No questions. Then the next session I'm going to discuss about bridge articulation. I will promise you that lecture is not going to go 3.5 hours, because I spend a lot of time to prepare these slides, and I spend a lot of time to explain you, because if you don't know what you are designed for, why you choosing this load, how you're going to apply them, how important they are, and then you can design bridges. So that's what I explained to you. And then the next session, we're going to discuss about bridge articulation. You should know the bridge articulation before we start modeling a bridge. If now you know the components of the bridge and the loading on the bridge, and if you know the bridge articulation, how the bridges behave with this loading, and how we're going to support them, connect them with substructure, superstructure, then you can easily design a bridge, because the analysis and design is a straightforward process. Any structural engineer can do that one, because you analyze, you use the design standard to design the design for bending, shear, torsion, axial. That's it. Yeah. And the next session we're going to discuss that one. So then I want to thank you, Chatumi and Dilina, for helping me to organize the presentation, and CSEC. So organizing this and recording this one for people to, anyone, if you want to go back and listen to this presentation again. And thank you very much for participating for today's sessions. So see you in next week, and have a good weekend. Good night.
Thank you, sir.